Good evening to one and all. Good evening. So please kindly confirm audio video on screen once. Please kindly confirm audio video on screen. Okay. Yeah. So let's start the session. Of course, till yesterday, what we have discussed is what are the different types of faults in the view of the what we call time period up to which the fault is going to occur in the system. We said we have two types of faults. One is a momentary fault. Next one we are saying as permanent fault or sustained fault. Okay. So now I am going to take up the heading like what are the causes for practical causes for short circuit faults in the system. Okay. So the next heading I am going to give here is practical causes for short circuit faults in the system. Short circuit faults in the system. Tell me, what are the practical reasons to get the short circuit fault? What are the practical reasons to get the short circuit fault? Anybody? The majority of the faults, particularly I am talking about extra high voltage lines and ultra high voltage lines. Majority of the faults, what we are going to get in the system are mainly due to insulation failure. Okay, maybe if you have some tower, something like this, I will say it's a transmission tower and it was a power conductor. Between the transmission tower and power conductor, we have some insulator, something like this. Some insulator string I am showing, right? And of course, you know, this tower is connected to ground. Tower is connected to ground, and this is a conductor. That's a conductor. See, whenever this conductor is experiencing a over voltage, definitely that insulated string what we have is going to be experiencing that over voltage because of that heavy stress experienced by the insulated string. We can experience some sort of flashover for the insulated string. So insulation flashover will cause for a conductor to ground fault. So majority of the short circuit faults what we get in the system are of this type only, which are going to be known as arcing faults in the system. Okay, so I can say first cause insulation flashover. Or you can say arcing faults in the system. And this arc will have some resistance. Generally, arc in the sense it's a fire, right? Flashover, or you can say it is fire. It's a fire. So I can say it might have some resistance of R arc. It might have a resistance of R arc. We can see. Okay, arc resistance R arc. Fine. So other reasons to get the short circuit faults in the system, maybe falling 3 branches on the conductor, right? So I said yesterday some of the things for you. So I'm writing them. 3 branches, falling 3 branches on the conductor, falling 3 branches on conductor. Tree branches in the sense it may not be a what's it called tree branch in the sense it may not be wood, dry wood. So if it's a wet wood, live tree, then that will be acting as a conductor. Live wood or live tree is going to act as conductor. That may cause for the short circuit fault in the system. Okay, yeah. And next type of short circuit fault will be snake faults. Like as we said earlier, snake falling on 2 conductors creating a short circuit fault on the system. Snake faults. And next one we can say mechanical failures. Mechanical failures may also cause for the short circuit faults. Particularly, I can say if cross arm position got disturbed, if the position of the cross arm got disturbed, definitely we can experience a short circuit fault between the conductors, right? Mechanical failures will cause for a short circuit fault. Mechanical failures. Next one. Next one we can say. Next one. Uh, as we said earlier, particularly during winter season, the conductor may be stretched. Conductor may be stretched, and obviously, if the conductor is getting stretched or contracted, conductor may cut into two parts, and conductor may fall onto the ground. That is obviously a creation of short circuit fault, which we can consider into a mechanical failure. Which we can consider into a mechanical failure. And I want to tell one more thing to you. One more thing. Just listen. Just listen. See, generally, at which part of system, if fault occurs, we feel that as a major fault or most severe fault. At which part of system, if the fault occurs, we will feel that fault as a severe fault. Generally, it is fault on the bus bar. Fault on the bus bar. I will explain stability. In the view of system stability, I am saying that fault on the bus bar is treated as a most severe fault. Okay, I will write in the next slide. Fault on bus bar. Fault on the bus bar is most severe in bracket with respect to stability of the system. With respect to stability of the system. Okay. Next thing. Kindly listen. Next thing I am going to tell you. See, generally, I am asking the same question again. Generally, if there is a short circuit fault on the system, who is the cause for the short circuit fault? Generally, if there is a short circuit fault on the system, who is the cause for the short circuit fault of the system? That is due to insulation flashover, I said just. Okay, and try to link up these two statements. If you have a fault on the bus bar, it's a most severe fault. And if there is a fault on the bus bar, that might be again due to insulation failure only, right? That might be again due to insulation failure only. So to overcome the fault occurrence on the bus bar because of the insulation failure, we have to maintain this bus bar insulation level as high as possible. Following the thing. That's why among all insulators at a given voltage level, bus bar insulator strength required must be very, very large. Very, very large. Okay. Yeah. So to overcome or to avoid fault on bus bar due to insulation failure. The bus bar insulation level shall be maintained as very high. Shall be maintained as very high. Shall be maintained as very, very high. All of you getting this one? Shall be maintained as very, very high. Yeah. Next thing. So by this statement, I can say simply that we don't have any possibility of getting a fault on the bus bar. We don't have a possibility of getting fault on the bus bar as you are maintaining that insulation level as very, very high. But particularly in some areas, in some parts of our country, we used to have large tail monkeys. Unfortunately, if that monkey comes and sits on the bus bar, and the tail of that monkey, large tail, we said, oh, the tail may be in touch with some conducting body that will lead to a short circuit fault on the bus bar. So practically, fault occurrence on the bus bar is mainly due to monkeys, or you can say monkey faults on the bus bar is one of the way of getting short circuit fault in the system. Okay, so in the previous slide, I'm going to write fifth one, bus bar faults, or you say monkey faults on the bus bar. Simple. Monkey faults. Monkey faults on bus bars. Monkey faults on bus bar. Okay. Right. So these are some of the practical reasons to get the short circuit faults in the system. Now we are going to discuss about what are the different types of short circuit faults in the system, particularly with respect to three-phase system. I am going to. Okay, so I will move with the next slide. So I will take the heading as types of short circuit faults. Types of short circuit faults in the three-phase system. Types of short circuit faults in the three-phase system. Yeah, simple. We have three conductors here: phase A, phase B, phase C. Yeah, I will show in the next slide. I will show in the next slide. Anyway, I will clear this one. I don't consider it further. So phase A conductor, it's a phase B conductor, and it's a phase C conductor. Okay, and it's a ground, we can say. Ground, some. What is the first type of fault you can experience? For the first type, any one phase is connected to ground. Maybe a tree branch falling on one conductor, causing that conductor to ground fault. Okay, so I can say A to ground fault or phase to ground fault. Else we can say sometimes as single line to ground fault. Single line to ground fault. Okay, so first type of short circuit fault is phase to ground fault. Phase to ground fault, or you can say single line to ground fault. Single line to ground fault. In the sense, either A is connected to ground, you can say. I will write in a new color. A is connected to ground, or phase B is connected to ground, okay, or phase C is connected to ground. Anyone, not all the three, any one among these three. Either A is connected to ground, or B is connected to ground, or C is connected to ground. That is a single line to ground fault, or you can say phase to ground fault. Second one is a phase to phase short circuit. Means any two conductors are shorted. Maybe AB got shorted like this, or you can say BC got shorted, or you can say CA got shorted. Okay, phase to phase fault, or you can call that as line to line fault. Okay, yeah. So second one is phase to phase fault. Phase to phase fault in the system. In bracket, call line to line fault, or you can say double line fault also. Or else you can say that as double line fault. Okay, Suresh, generally bus bars are in panel boards, then how monkey faults occurs? See, actually these bus bars are going to be installed in substations, right? Maybe in power grid, or you can see 400 kV by 220 kV substation. And if it's an outdoor substation to you, definitely these bus bars are kept open air, in an open air. So definitely there is a chance of getting the short circuit fault on the bus bar due to monkeys. Okay, next one. See, this phase to phase fault I'm going to name as A to B short circuit, AB conductors getting shorted by some means, or you can say BC conductors got shorted, BC conductors got shorted, or you can say CA conductors got shorted. So AB short circuit or BC short circuit, or you can say CA short circuit. And other type of short circuit fault you can say phase to ground, phase to ground. Else you can say double line to ground fault. Any two phase conductors, phase to ground, or in bracket you can call double line to ground fault. Double line to ground fault. Okay, means you can call here AB connected to ground, or you can say BC connected to ground, or you can say CA connected to ground. AB connected to ground, BC connected to ground, or you can say CA connected to ground. Vaishnavi, I will come to your doubt in the doubt session. Many of the people might be having it. Bus bar is nothing but connection between number of lines. Connection between number of lines. Maybe I will show. If this is some rectangular crosser, we have rectangular crosser, and generally we used to keep some insulators on this crosser. The insulators on the top of these insulators, we keep some conductive element like this, which will give interconnection between some number of incoming systems and outgoing systems. Which will give interconnection between number of incoming and outgoing systems. This is going to be called as a bus bar. Going to be called as bus bar. Okay, bus bar is simply as a node in the electrical circuit, but it's a what we call a simple rod which will have interconnection of many number of transmission lines. Okay, let's continue. Next type of fault what you can experience is three-phase fault. All the three conductors got short circuit. That we can say three-phase fault. Yeah, so I am removing this slide. I will write here that is fourth one. Three-phase short circuit. Three-phase short circuit fault. Short circuit fault means ABC conductors got shorted. A, B, C conductors got shorted. You can call it is triple L fault sometimes. Call this as triple L fault. And fifth one, you can say, three-phase to ground. Three-phase to ground means ABC shorted to ground. Three-phase to ground fault. Three-phase to ground fault. Okay, so I'll call this as a triple LG. Or else you can say A, B, C connected to ground. A, B, C connected to ground. You can say. Yeah, I'll do it. Maybe for next class I will prepare with this headphones and all. Yeah, next thing. Listen. So simply we have 5 types of faults here. Let me list out them: LG, LL, double LG, triple L, triple LG. That's it. Okay. I will try to explain about these 5 now. Look here. This is some three-phase power system network. Three-phase power system network. I have 3 wires outcoming: phase A wire, phase B wire, phase C wire. Look. 3 wires outcoming. 3 wires outcoming. I am saying A, B, C. Fine. Next. It is at no load. Before occurrence of short circuit fault, this particular 3 lines, what I have taken now, are under no load condition. No load condition means what? A current will be 0, B current will be 0, C current also 0. That's the situation in the pre-fault operation. This is assumption. This is assumption what we are considering. Now, let us say the same system I have repeated. And let me clean these 3 first. Yeah, let's have a look here. For example, if I have A to ground fault in the system, in this particular 3-phase system, if you have phase A to ground fault, then what will happen? Tell me anybody what will happen first. If phase A conductor is getting grounded, what will happen? Phase A voltage will become 0. Phase A conductor is getting grounded means phase A voltage will become 0. Whenever this phase A, this terminal voltage becomes 0, we have a huge potential gap. We have a huge potential gap. Because of that, we have some current circulation in the conductor A. What about the conductor B and conductor C current? Mridul Sharma, tell me the answer. Mridul Sharma, please tell me the answer. What is the conductor B and conductor C currents? Conductor B and conductor C currents, how much? 0. I said previous currents are 0, right? I said pre-fault currents are 0. Now, if the fault occurred on phase A conductor, only conductor A will carry the current. B and C currents will be 0. And means all the 3 conductors are not carrying equal currents, unbalanced currents. Means system is becoming unbalanced if you have a line to ground fault in the system. Because of line to ground fault in the system is becoming unbalanced. All of you getting me? Now again, if I take a double line fault, something like this. Double line fault, if I take something like this, then we have some current in the A and we have some current in the B and C current is 0. Only A and B are carrying currents. C current is 0. Again, the system is unbalanced only. Again, if you have double line to ground fault, something like this. Double line to ground fault and A and B are carrying currents, C current is 0. A and B are carrying currents, C current is 0. Again, the system is becoming unbalanced. Means what I can say here is, this LG, LL, LLG. These three are making the system as unbalanced after the fault occurrence. Making the system as unbalanced after the fault occurrence. Hence, we are going to name these faults as unbalanced faults, or you can say unsymmetrical faults in the system, right? These are going to be called as unbalanced or unsymmetrical faults. Unbalanced, or you can say these are unsymmetrical faults. Okay, next thing. For example, if you have triple L fault in the system, before occurrence of the fault, currents are 0 here. Now the fault occurred on the 3 wires. Then obviously you have phase A current something, phase B current something, and we have some current in the C also. We have some currents in the A, B, C like IA, IB, IC. Then if there's a three-phase fault on the system, what I will feel simply is we are putting a 0 amount of load on the transmission. Means 0 impedance load. Better term is 0 impedance load on the transmission. Then obviously all the 3 phases are experiencing 0 impedance as a load. Means 3 phases are getting balanced load detected. Means if you have a triple L fault on the system remains in the balanced state. So obviously triple L fault we are going to name as balanced short circuit. And if you have triple line to ground fault, what you can say? If you have triple line to ground fault, what you can say? Then also the system will be balanced to 3. Means this triple L and triple G faults we are going to call as balanced or symmetrical short circuit faults in the system. Symmetrical short circuit faults in the system. Okay. So actually, according to the nature of system after the fault occurrence, we are having 2 types of faults again. One, it will be balanced fault in the system. Second one, we are saying unbalanced fault in the system. Okay. Next, one more simple discrimination I want to tell between triple L and triple G. Okay, as a statement I will tell right now, but why in the sense we are going to get at the end of the fault analysis. Right now I can't explain it. Tell me now. This is a pre-fault system. Listen. This is a pre-fault system. All the 3 currents are 0. 3-phase fault occurred. Then it's a balanced fault, as I said just now. IA, IB, IC currents are balanced. Means magnitudes of 3 currents are equal and displaced by an angle of 120 degrees. Clear? 3-phase to ground fault occurred. See, if the 3 currents what you have IA, IB, IC are balanced, what will happen to the ground current value? Anybody please tell me? What will happen to ground current value? It is IA plus IB plus IC. As it is a balanced current set, sum of the 3 currents will be 0. Clear? Okay. Next, tell me please. Means ground current is 0 here. If ground current is 0, even though the fault is a triple line fault or triple line to ground fault, it makes no difference in the steady rate. Means what I have to tell here is triple L fault and triple L G faults are identical. We don't have any change in the analysis as well as we don't have any change in the value of the fault current. Provided that the pre-fault system, what do you mean by pre-fault? Before occurrence of the fault, right? The pre-fault system is balanced one. Pre-fault system is balanced one. Okay? Yeah. So I will write here. If pre-fault system is balanced, then triple LG is identical to triple L. Triple LG fault is identical to triple L fault. But listen. If the pre-fault system is unbalanced one, means before occurrence of the fault itself, the system is unbalanced. System is unbalanced. In that particular state, triple LG fault will become more severe than triple L fault in the system. Okay, anyhow, I am writing that statement. I said you, I don't explain the statement right now. I will be taking up the statement at the end. So I'll say here, if pre-fault system is unbalanced, then triple LG becomes more severe than triple L fault. More severe than triple L. Dopati Bhavani, we will be clear that out later. Area, if you want, I will tell now itself. Does the severity of short circuit fault is same on each conductor? Obviously, if all the three currents are equal in magnitude, definitely severity of the fault will be equal in the phase A, phase B, and phase C. Okay? Yeah. Next thing. This is about classification of faults. Next, okay, in the same topic, I want to tell you what's the probability of fault occurrence. Okay, I'll write number of faults what we have taken: LG, LL, double LG, LL. Okay, probability of fault occurrence. Generally, 70% of short circuit faults what we get in the system are LG faults. 70% of the short circuit faults what we are getting on the system are LG. And 15% of the faults generally we get in the nature of LL. And 10% of the faults we get in the nature of LLG. 5% of faults will be symmetrical in nature. Triple L and triple LG. This is one type of statistics I am giving. But each textbook will give their own statistics. In some of the textbooks I have seen, LG fault they said 80%. Okay, LL fault they said some 10%. Okay, some numbers they said. Okay, these are some numbers, but according to these things, only one thing what I am asking you to remember is LG fault is more common. Majority of the faults what you get in the system are LG in nature. Okay, very less components of faults we get in the nature of triple L or triple LG. Okay, so I can say LG is most common fault in the system. Most common fault in the system. Whereas triple L or triple LG, these are least common faults in the system. Least common faults in the system. Least common faults in the system. But in the view of fault current magnitude, or in the view of severity, or in the view of fault current magnitude, if you think triple L fault will become more severe as compared to LG fault. Okay, so according to severity, so LG fault is most severe fault. LG fault is least severe fault, and triple L and triple LG are most severe faults in the system. Most severe fault means LG is most common and least severe fault. Least severe. I'm saying this statement in general. For example, if you have some numbers, and if you have a capability of doing fault analysis with those numbers, do the fault analysis. And check which fault is more severe. Is it LG, LL, LLG, or triple L? Following all of you. Here I am saying in general, LG is a least severe fault and triple L is a most severe fault in the system. Most severe fault in the system. At different locations, if you study, the severity of the fault level may be changed. Definitely. Okay. At that specific point, I will discuss about it. But this is in general. Okay. Yeah. Next thing. The next thing I want to discuss here, what's the aim of doing fault analysis? What's the purpose of doing the fault analysis? That we are going to think. Yeah, so I'll take in the next slide. Next slide. Purpose or aim of doing fault analysis. Fault analysis. Purpose or aim of doing the fault analysis. Okay, next. Listen. Purpose or aim of doing the fault analysis I am writing now. Many of you might be knowing what's the aim of doing fault analysis here. What is the aim of doing fault analysis? Simple, to design the protective switchgear. Because if the fault current flows for a long amount of time in the system, there is a possibility of damage for the equipment, maybe thermal damage, or technically we have some damage like loss of synchronism and all. Loss of synchronism or loss of stability and all. Okay, to overcome those issues, we have to disconnect. We have to disconnect the faulted part from the system as quickly as possible. As quickly as possible. For that purpose, we are going to design the protective switchgear, means relay and the circuit breaker. Okay, so main aim of this fault analysis is designing protective switchgear. Protective switchgear means you can say relay and the circuit breaker. Relay and the circuit breaker combinations. Okay. Relay and circuit breaker. Okay, next. First I am going to tell you about relay setting selection. Relay setting selection. Some brief I am going to give about this. Relay setting selection. Okay. See, this is one system I have. Just it's a single phase system. You feel if you want. See, I am keeping that relay and the circuit breaker combination. Relay and circuit breaker combination at this particular location. This is a relay and circuit breaker combination. See, actually, the assignment what we are saying for this relay, is you have to identify the fault occurring on this transmission line wire. This anywhere if you have a fault on this transmission line wire, this relay should identify it. Okay, so this is the protective zone given for that protective. Is a protective zone assigned for the protective. Let me continue. Next thing. Listen. See, actually, as a basic term, I have to tell you. Look here. Based on what fault we have to select the relay setting. Relay setting means you simply say pickup current for your understanding. If you want to say this is simply pickup current selection. Based on what fault we have to select the pickup current. Is it least severe fault or most severe fault? That will tell me first. Pickup current selection will be done based on least severe fault or most severe fault. Least severe fault. Listen here. See, if you select your relay setting based on the least severe fault, then it is capable to identify the most severe faults also, right? Yes or no? In that perspective, always we should select it based on the least severe fault. So I'll write here relay setting selected based on least severe fault. Okay, selected based on the least severe fault. Okay, done. Next. Actually, fault current value not only depends upon the type of the fault. Means for LG fault, you get some value of fault current. LL fault, you get some value of fault current. Triple L fault, you get some value of fault current. Not only that, according to the position of fault occurrence, at what location the fault occurred, at what location the fault is going to occur. Based on that also, the value of fault current will be changing. Okay, tell me, in this particular protective zone, at what location the fault current is minimum? At what location of fault the fault current will be minimum? Anybody please tell me, at what location of fault the fault current will be minimum? Is it nearby the breaker or at the end? At the end of the protective zone? Definitely at the far end. At the far end. Why it is so means it will have some impedance, right? It will have some impedance. And if you take fault at the end, this total impedance, and this voltage you take, voltage by this total impedance will give the fault current. But if you take at the middle, only half of the line impedance is going to be offered to the fault current. So voltage by this half of the impedance obviously makes the fault current double. Makes the fault current double. So if you are moving from far end towards the relay location, towards the relay and circuit breaker location, fault current value is going to be increased. So for which location of fault we should select the pickup current? Far end. Simple. We have to decide what is our protective zone. Then we have to select what is the least severe fault. And you have to take that fault at the end of the protective zone. Calculate that current value. Based on that current, we have to select the pickup current. If you do like that, for any type of fault occurring at any point inside this protective zone, the relay is capable to identify the fault. The type of characteristic we should provide for the relay. The type of characteristics we should provide for the relay by means of this relay setting selection or pickup current selection. Okay, yeah. So look here, relay setting selected based on least severe fault occurring at the end of protective zone. At the end of protective zone. At the end of the protective zone. Is it clear? Is it clear? Next we'll think about this breaker rating selection, circuit breaker rating selection. Second one, circuit breaker rating, or you can say breaking capacity of the circuit breaker. Circuit breaker breaking capacity selection. Breaking capacity selection. Okay, circuit breaker rating selection. Else you can say that as breaking capacity of the circuit breaker. Breaking capacity of circuit breaker. Okay, tell me now. Tell me. Based on what type of fault you should select the breaking capacity of breaker? Based on what type of fault you should select it? Is it based on least severe or most severe? Most severe. Why it is so means I will tell you. See, we should select the circuit breaker contact size. Circuit breaker contact size in such a way that the circuit breaker contact should not be melted down. Should not be melted down for any value of breaking current. For any value of breaking current, it should not be melted down. So we have to design those breaker contacts based on the highest value of fault current. Highest value of fault current. By selecting that based on the highest value of fault current, obviously, even though it is opening for lower values of fault currents, breaker contacts are not going to be damaged. Okay, so I can say circuit breaker rating. Circuit breaker rating will be selected based on most severe fault. Most severe fault. Circuit breaker rating will be selected based on most severe fault. Rupturing capacity, breaking capacity, both will be same. Getting confused with least severe? Simple, Rakesh Kumar. Whichever the fault is giving low fault current, that is least severe one. Whichever the fault is giving high fault current, highest fault current, that's the most severe one. That's it. If you are selecting the relay, go for the least severe fault current. Why in the sense, if you select the pickup current based on that value, then the relay is capable to identify remaining all also. What do you mean by pickup current? It is a current value beyond which the relay will sense that as a fault. Na? For example, if you select the pickup current based on the highest fault current value, then it may not have a capability to identify lower levels of fault current. Lower levels of fault current. Following all of it. For example, if you select the breaker rating based on the lowest fault current value, whenever it is interrupting high fault currents, breaker may damage. So, breaker has to be selected based on the highest fault current value. Relay setting or pickup current has to be selected based on the lowest fault current value. Okay, all of you understanding this one? Yeah. Next, most severe fault. Generally, this fault current is highest for which location of fault now? Location. At what location we should consider the fault to design the breaker? Nearby the circuit breaker. Nearby the circuit breaker we have to consider. Okay, nearby the breaker you write. Most severe fault occurring nearby circuit breaker. CV location. Generally, most of the circuit breakers what we have in the system, are three-phase circuit breakers only. Three-phase circuit breakers. Okay. So the three-phase circuit breaker rating or breaking capacity formula I am going to give you. Okay. I will write here three-phase circuit breaker rating or breaking capacity. Breaking capacity formula. Very simple one. Formula I am going to call here. Listen my words. Just follow the terms what I am saying. Don't be in doubt. Just look here. Capacity in the sense I have to give this number in terms of MVA. I have to give this number in terms of MVA. I'll say in bracket MVA. What's the formula for three-phase power generally? Apparent power. What is the formula for three-phase apparent power? 3 into phase voltage multiplied with the phase current. Magnitudes. 3 into phase voltage magnitude into phase current magnitude. That's it. That I am writing. 3 into phase voltage magnitude multiplied with phase current in the sense, how much current the breaker has to interrupt. How much current the breaker has to interrupt. That we have to consider now. Okay. So I'll write here ICB modulus. Where this ICB modulus is a RMS current to be interrupted by the breaker. To be interrupted by the circuit breaker. RMS current to be interrupted by the circuit breaker. Okay. In terms of kiloamperes, you take this current, and this phase voltage is a rated voltage of the circuit breaker. Rated voltage, of course, per phase. Rated voltage per phase. You take this in kilovolts. So kilovolts into kiloamperes, it will come in megavolt amps. Megavolt amps. Okay. Most severe means it's not maximum time. I said value of fault current is a thing which is deciding the severity. Value of fault current is a thing which is deciding severity right now. Diksha. Okay. Next, just I will try to rewrite this formula. This formula only. Breaker rating. CB rating, three-phase or breaking capacity. CB rating, three-phase value equal to. Look here. 3 into this B phase I will take in per unit form. ICB also I will take in per unit form. Else I will write reverse. Better in a clear understanding I am taking. V phase per unit into V base per phase. Is it okay? This is a phase voltage into breaker current in per unit into I base per phase. Okay. Circuit breaker current in per unit into phase current per phase. What is this now? 3 into phase voltage in per unit form multiplied with the circuit breaker current in per unit form multiplied with what now? V base per phase into I base per phase is what? V base per phase into I base per phase means S base per phase. S base per phase. So the 3 into S base per phase is nothing but S base 3 phase. So V phase per unit into circuit breaker current to be interrupting current of breaker per unit into S base 3 phase. Like this also you can write the circuit breaker rating formula. Circuit breaker rating formula. Yeah, that's what I am saying you. Sometimes we have single phase breakers used. Sometimes single phase breakers use single pole breakers, we say. But the breaker what we are saying here is 3 pole 3 phase breaker. 3 pole 3 phase breaker. At a time, all the 3 poles will be opened up. At a time, all the 3 poles will be opened up. That's the type of breaker what we are discussing here. Okay, yeah, done. Next thing. There is one more term. Generally, we have a confusion between this term breaker rating and fault level, or you say short circuit MVA. Fault level, or you can say short circuit MVA. We have some difference between these two terms. Okay. Anyhow, first I will write the formula for the fault level. After that, I will tell you what is the difference between the fault level and the breaker rating. Yeah. So I will take in the next slide. Here, fault level or short circuit capacity or short circuit MVA, all these terms are identical to concept. Short circuit fault level, or you can say short circuit capacity, or you can say short circuit MVA. Very simple formula, very simple formula. Fault level is equals to, look here, 3 into pre-fault voltage magnitude in kilovolts per phase. BPF means pre-fault voltage. I'll write that also. You may ask him again doubts. Pre-fault voltage. Pre-fault voltage means simply before occurrence of short circuit fault, how much voltage you have at the location of fault. How much voltage you have at the location of fault before the fault has been occurred. Multiplied with fault current magnitude in kiloamperes. Fault current magnitude in kiloamperes. Fault current magnitude in kiloamperes. Else we can write this same as BPF in per unit form into fault current per unit form into S base 3 phase. Similar to the previous one. Yes or no? Fault level in terms of MVA. Fault level in terms of MVA. For any type of fault it is. For any type of fault. Is it a single line to ground fault? Double line to ground fault? Double line fault? Triple fault? For any type of fault, the same formula we are going to write. Same formula we are going to write. Okay? 3 into pre-fault voltage in kilovolts into fault current in kiloamperes. Else, pre-fault voltage per unit into fault current per unit into S base 3 phase. You write here for any type of short circuit fault. Any type of short circuit. Getting? Next one. Second line is also absolute value for 3 phase fault only. Second one is again absolute value of 3 phase fault. Okay, fine. Just the already I have written something in the previous slide that I have extended. Okay, 3 into you have to write again pre-fault voltage per unit into V base per phase, fault current per unit into I base per phase, V base per phase into I base per phase is S base per phase, 3 into that is S base. Like that you have to write. Yeah. Next thing. Sometimes in the examination, we used to get a question like, what is the fault level value per unit form? What is the fault level value in the per unit form is nothing but simply fault level in MVA by S base 3 phase. Fault level in MVA by S base 3 phase means V pre-fault per unit into IF per unit. Okay, I'll write fault level in bracket per unit, nothing but absolute value of fault level, absolute value of fault level by S base V base number. If you take up that, it will be pre-fault voltage in per unit form multiplied with fault current in per unit. Multiplied with fault current in per unit form. For example, sometimes this pre-fault voltage may be equals to rated voltage. Means if the pre-fault voltage equals to 1 per unit, pre-fault voltage equals to 1 per unit, at the time this fault level in per unit is nothing but fault current in per unit itself. Okay. So if pre-fault voltage per unit is equals to 1 rated voltage, then fault level in per unit is nothing but fault current magnitude in per unit form. Fault current magnitude in per unit form. Yeah, RMS per phase current. Mudrid Vasista. Yesterday you said that you are not getting a chance, but I am not leaving the class without clearing all your doubts. You are leaving the class first, right? Please wait till the end. You will get a chance to ask the doubts. Yeah. Next. Let's continue. So in the examination or anywhere, if sometimes if they say that fault level is some 10 per unit, fault level is some 10 per unit, we have to assume that as fault current magnitude in per unit form. Fault current magnitude in per unit form. Okay. Next thing. Let's have some difference between these things: breaker rating and fault level. Circuit breaker rating versus fault level. Fault level. This I am going right now. By taking one small example, I will try to explain this. This is one system we have. One. And this is some other system like this. Between these two systems, we have one transmission line link. Maybe short conductor, maybe 1 kilometer length or even less than that. Some link we have between system 1 and system 2. Between system 1 and system 2. Just we have one link. Next, look here. Very simple statement. Don't confuse. Stop writing. Just listen here. This is one breaker we are keeping. Circuit breaker. I will give time to write. Just listen. This is one breaker I am keeping. I want to design that circuit breaker rating. I want to select the rating of that circuit breaker. Then what you have to do is, we should take fault nearby the breaker location. Okay. I have taken fault nearby the breaker location at this place. At that place, I have taken the fault. Then see, on left side we have one system. Means in that system we have some generators, transformers, transmission lines. Right side we have one system that will have again some generators, transformers, transmission lines. See, definitely the first system will supply some current towards the fault element. Second system also supplies some current towards the fault element, and the resultant current is flowing into the fault element. Resultant current is flowing into the fault element. Okay, next thing, listen please. System 1 may be supplying a current of IF1 to the fault. System 2 might be supplying a current of IF2 into the fault. And here it is IF1 plus IF2 as a fault current value. Fault current value is nothing but IF1 plus IF2. Clear? Tell me, very simple question, very simple question to you. How much current the breaker has to interrupt now? What is the amount of current the circuit breaker has to interrupt? Is it IF1 value or IF2 value or total fault current? What current the breaker has to interrupt? Is it IF1 or IF2 or IF? How much? It will be IF1 only, right? Huh? Don't tell the answer by keeping something in your mind. Always a breaker is interrupting fault current, breaker is interrupting the fault current. what current is flowing in the breaker, that you check. What current is flowing in the breaker, that you check. That current, the breaker has to interrupt. How much current? IF1 current only flowing in the breaker. IF2 is not flowing into the breaker, right? IF2 is directly flowing into fault element. Getting me? So I can say this breaker in this particular case, circuit breaker need to interrupt a current of IF1. Circuit breaker need to interrupt a current of IF1. Same diagram. I will repeat in the next slide. Please take this one quickly. Please take this one. I'll wait for 10 seconds. Please write this one quickly. If you have completed, please raise your hands. Good. Same system on this side. On this side. And this is a link. And this is a circuit breaker. Circuit breaker. Same system, no changes. But I am locating the fault above the breaker. I am locating the fault at this place. In this place, I am locating the breaker. Now you see, do we have any change in fault location? In the electrical circuit point of view, do we have any change in the fault location? I don't think so. I don't think so. Why? I am showing previous time. Why? Why we don't have any change in the fault current value? Why? In the sense, the circuit breaker impedance can be neglected, right? Circuit breaker impedance can be neglected. By neglecting that, even you take fault before the breaker or after the breaker, you don't have any change in the current supplied by system 1 and system 2 into the fault. So obviously, system 1 will supply a current of IF1 here. System 2 will supply a current of IF2, and resultant current flowing into the fault element is same value as it is we have mentioned. IF1 plus IF2. IF1 plus IF2. Can anybody tell me how much amount of current the breaker has to interrupt in this case? How much current the breaker has to interrupt in this case? IF2 current the breaker has to interrupt. So in this case, I will write circuit breaker current equals to IF2. IF2. Now tell me, in the first case, breaker is interrupting IF1 current. Second case, it is interrupting IF2 current. See, for any current interruption, breaker should not be damaged. For any current interruption, either it is interrupting IF1 or IF2, breaker should not be damaged. Then, based on what current we have to select the breaker rating? Based on what current we have to select the breaker rating? Highest among IF1 and IF2. Highest current among IF1 and IF2. Yes or no? Clear? Highest, greater of the two we have to consider. Now, this circuit breaker rating, if I write, this is 3-phase. Okay. Phase voltage value in the per unit form into maximum of IF1 magnitude, IF2 magnitude, IF1 magnitude, IF2 magnitude in per unit form into S base 3-phase. Like this. Phase voltage per unit value multiplied with maximum value of two fault currents, IF1 and IF2, multiplied with S base 3-phase. That is the breaker rate 3-phase. What is fault level? Anybody tell me what is fault level here? Yeah, what is fault level? Fault level 3-phase. Formula. Default voltage per unit into what? Into, is it IF1 or IF2 or IF? Is it IF1, IF2 or IF? IF, only fault current you have to consider now. It is a summation of IF1 and IF2. Getting me? Please tell me. This is a fault current magnitude in the per unit form into S base 3-phase we have to consider. S base 3-phase. That's the fault level in 3-phase. This is a difference you have to observe between the breaker rating calculation and the fault level. Okay. Yeah. So anyhow, I will try to explain the similar concept in a numerical problem. So next, I am going to take up quickly what are the various assumptions we are going to consider in the fault analysis. Assumptions in the fault analysis I am going to take up. Yeah. So I'm moving with the next slide. Next slide I am taking up. Assumptions. Assumptions in fault analysis. Assumptions in the fault analysis. Yeah. First assumption. See, all the time, whenever we do this type of analysis, maybe fault analysis, stability. But sir, how CB will operate it? Fault is occurred before CB. What? Anusha, we are fault level means fault current magnitude only, Dinesh. Fault level means fault current magnitude. How much MVA? How much MVA the system is having a circulation. But sir, how the circuit breaker will operate? Fault is occurred before CB. That's what I am saying you. Whenever the relay senses the fault, it will give a command to the breaker. Breaker is going to open. Whenever the breaker is opening, breaker should not damage. Breaker should not damage. Breaker should not damage means we should check how much highest current it has to interrupt. Based on that current, you have to select the breaker rating. That's it. Okay, listen. First assumption will be always representation of the generator. Okay, so generator represented with subtransient EMF source. Subtransient EMF source. Transient EMF source. In bracket, you write EG double dash. Subtransient EMF source, EG double dash. Behind its direct axis, subtransient reactance. Okay, so you can call it is XD double dash. XD double dash means the generator is going to be represented with the JXD double dash impedance with a voltage source. Voltage source, I am calling this is EG double dash. EG double dash. Okay, see, if you have a resistance, you consider that resistance in the network. If you don't have resistance, you no need to consider the resistance in the network. Jayant, I have not taken total fault current in the breaker rating. I have not taken the total fault current in the breaker rating. I have taken the fault current only in the fault level calculation. Okay, let's continue. This is the generator representation. I will discuss about the EG double dash, the problem. Second, transformer and transmission line generally represented with series impedances. Series impedance. Shunt elements are neglected in these two, and shunt elements are neglected, represented as series impedances, and shunt elements of transformer and transmission line are neglected. Transformer and transmission line are neglected. Okay. Next. See, if you have a resistance in the network, definitely you should consider the resistance in the fault analysis. You should not neglect it. If you have some resistance for line, resistance for generator, resistance for transformer, we should not neglect it. We have to consider it. Okay. Yeah. Next assumption I can say. See, for example, we have a generator here connected to one transmission line. Look all of it. And here I am keeping some synchronous motor. I said synchronous motor symbol is round with the M inside the round symbol. Yeah. So it's a synchronous motor. It's a synchronous generator we have. Very simple thing. Before the occurrence of short circuit fault, we might be having some power transfer from this generator to motor. We might be having some power transfer from generator to motor. Now, all of a sudden, at some time, fault occurred at the motor terminal. Means this terminal voltage was falling down to zero. Terminal voltage was falling down to zero. See, if the terminal voltage was falling down to zero, this generator voltage and this zero having a large gap, because of that, this generator will supply the fault current definitely. There's no doubt about it. Following all of you what I'm saying. Simple. Fault occurred at some location. Generator voltage is a high value. We have a potential gap. Because of that, fault current is circulated by the generator. See, whenever this voltage is zero, what is the power input to the motor? What is the power input to the motor? That will be zero, right? Real power input to the motor will be zero. See, whenever the power input to the motor is zero, power input to the motor suddenly or instantaneously falling down to zero, can we expect that rotor speed will fall down to zero instantaneously? Can we expect that the rotor speed will fall down to zero instantaneously? No, we don't expect that rotor speed will fall down to zero instantaneously. You know the reason. I'll tell you. Listen. So whenever that fault occurred, all of a sudden voltage is falling down to zero. Input power to the motor equals to zero. But still, the rotor will continue to rotate because there is some kinetic energy. There is some kinetic energy stored in the rotor. Okay, because of the kinetic energy, it will continue to rotate. You know that field winding, particularly in synchronous motor, excited with the DC supply. Field winding in synchronous motor excited with the DC supply. Because of that, a DC field is rotating in the air gap, I can say. That will cause an EMF in the stator. That EMF definitely drives the fault current to fault element. Definitely, it will drive the fault current to fault element. Following all of you, I am writing those statements. Again, I will tell some more things to you. Listen. Just after fault occurrence, terminal voltage of synchronous motor, yes sir, suddenly falls down to zero. But still, yeah, the rotor will continue to rotate. But still, the rotor will continue to rotate. Due to kinetic energy stored in the rotor. Okay, as rotor field is excited with the DC supply, as a rotor field is excited with the DC supply, an EMF will be induced in stator, and it causes and it drives fault current to the fault element. And it drives the fault current to fault element. Up to how much time it will drive the fault current? Tell me please. Up to how much time it can drive the fault current? See, continuously this rotor is rotating and speed is decreasing. Speed is decreasing, right? So up to the time whenever the speed is reaching to zero, up to the time whenever the speed is reaching to zero, up to the time it is capable to supply the fault current to fault element. How much time it will take then? How much time it will take to say that speed is reaching to zero? Speed is reaching to zero. Let's have some estimation. Let's have some estimation. I'll say a typical rotor is taking some time, let us say 20 seconds. It's taking 20 seconds to get its speed from synchronous to zero. To get its speed from synchronous to zero, it is taking 20 seconds. 20 seconds means, is it a small time or large time? 20 seconds means, is it a small time or large time? Very large in power system analysis. In what units you measure the time? What units? Units of time is what? Cycles. We used to measure the time in cycles. 20 seconds. 1 second means 50 cycles. 50 cycles per second. Okay. So 20 into 50. 20 into 50, if you take, how many cycles you will have? 1000 cycles. 1000 cycles. So for 1000 cycles amount of time, this motor is going to supply the fault current to fault element. Following all of you, it's a huge amount of time. So definitely we have to consider the fault current supplied by the synchronous motor into the fault analysis. Okay, yeah. So I'll write here drives the fault current to fault element. So for a long amount of time, I'll write for a long amount of time. Long amount of time implies synchronous motor fault current supply shall be taken into fault analysis. Consider it into fault analysis. Consider it into fault analysis. Fault analysis. Okay. So these are some of the assumptions. For example, if you have induction motor there, in place of synchronous, if you have induction motor, what do you think I should say? If it's an induction motor, what I have to say? Fault occurred. Voltage fallen down to zero, but still there is some kinetic energy in the rotor. Because of that kinetic energy, rotor will continue to rotate. Induction motor rotor also continue to rotate, but there is no field excitation. If you don't have any field excitation, the induced EMF in the stator expected to be neglected. The induced EMF in the stator can be neglected. So the induction motor may not drive any fault current to the fault element, or current supplied by the induction motor during the short circuit fault was completely neglected. Okay, yeah. So I'll write that statement also as a next assumption. Right. Fourth assumption. Fault current supplied by induction motor IM is neglected. Fault current supplied by the induction motor is neglected. Okay, next assumption. Frequency of system is assumed as constant. Frequency of system is assumed as constant during the fault analysis, during the fault current calculations. Frequency of system assumed as constant. Or you can say all the synchronous machines what you have, maybe generator, motor, what you have, these are rotating at synchronous speed. Okay, all synchronous machine rotors are rotating at synchronous speed. All the synchronous machines rotors are rotating at synchronous speed. Yeah. So these are some of the assumptions we are considering. Sometimes, particularly in problems, they may not give the pre-fault voltage. That we have to consider as 1 per unit. If they won't give any pre-fault voltage in the problem, we have to consider that as 1 per unit. Anyhow, I am not writing that in the assumptions. Okay. Yeah. Next. We have list of faults, right? LG, LL, LLG, triple L, triple LG. Before discussing about these types of faults, first I am going to discuss some basic concept as fault occurring on a no load operating transmission line. Please, we'll take one no load operating transmission line. We'll consider that short circuit fault. Okay, we will see what will happen. What are the transients occurring? What are the transients occurring in that? That we are going to discuss first. After that, we take one alternative. No load operating alternator. No load operating alternator. And again, we take a short circuit fault on that alternator. And we will see what are the transients we are getting during the short circuit on the alternator. Then we will complete little about the three-phase fault analysis. We'll do some problems on the three-phase fault analysis by completing alternate itself. Okay. After completing that, we will move to LG, LL, and LLG faults. All of you getting me? All of you getting the procedure what he said? Tell me please. Simple. First we'll discuss about short circuit fault on three-phase short circuit fault on no load operating transmission line. Then three-phase short circuit fault on no load operating synchronous generator. Okay. And we will almost complete the three-phase fault analysis with some problems. Then we will move to the unsymmetrical faults like LG, LL, and LLG. Yeah. So the first and foremost heading I'm going to consider further, that is three-phase short circuit fault. Three-phase short circuit fault on no load operating transmission line. No load operating transmission line. Three-phase short circuit fault on no load operating transmission line. Okay. So this is one source I am saying here. Source. And this is a transmission line wire. This is one transmission line wire, you can say. Transmission line wire. Operating under no load, we have mentioned no load. And we call this source as an ideal voltage source. It's an ideal AC voltage source without any internal impedance. Ideal AC voltage sourse. You call here in bracket, source impedance is equals to 0. No resistance as well as no reactance. This transmission line wire will have some resistance as well as reactance or inductance better. It will have some resistance as R I am saying, and it will have some inductance as L. These R and L are per phase resistance and per phase inductance of the transmission line. Okay, R comma L, these are per phase resistance and inductance of line. Resistance and inductance of line. Inductance of line. Okay, now I'm going to take a short circuit fault at the end of the transmission line. At the end of the transmission line, maybe at a time t equals to 0 plus. At a time t equals to 0 plus, we are experiencing a three-phase short circuit fault at the end of the transmission line. Okay, please listen to my words. Please listen to my words. Transmission line is operating under no load condition, supplied by a balanced voltage source. Supplied by a balanced voltage source. And all of a sudden, if you have a three-phase short circuit at the end of the line, whether your system is balanced or unbalanced, that will tell me first. Whether your system is balanced or unbalanced. It will be obviously balanced only, right? Balanced, unbalanced, it will be obviously balanced. Balanced means, can we do per phase analysis? Yes. So we will draw only per phase network, so-called phasor network, and then we will try to continue our study. I will write that statement also. So at time t equals to 0 plus, three-phase short circuit occurred at the end of the line. End of line. And the system is balanced. So per phase analysis can be done. Per phase analysis can be done. Per phase analysis can be done. So we are taking only phase A equivalent network. Phase A equivalent circuit we are taking up. So we have a phase A voltage source here. Phase A voltage source, and line is represented with a resistor and some inductance like this. And this is up to neutral. And this voltage I am showing as VA. Source voltage I am showing as VA. Resistance R, inductance value L. Resistance value R, inductance value L. Okay, next. See, at the end of the line, we have a short circuit fault. That fault, I am modeling that fault with a shunt element. Modeling that fault as a shunt element. Shunt switch, you can call it if you want. Shunt switch. Okay, so before the switch is getting closed, you don't have any current flow in the system. Means there is no current flow before the occurrence of short circuit fault. Once after the switch was closed, obviously we have a short circuit experienced by this source, and that will circulate the fault. So when the switch is getting closed, we are saying at the time t equals 0 plus, and whatever the current flow you have here is a phase A current, phase A fault current, phase A fault current can IA or IF, IA or IF. Okay. Next. Simple. We have to get the equation for IA here. That will tell you what are the various components you have, how this fault current is changing with respect to time, and all these things. First of all, let us take that VA voltage. Let phase A voltage VA. I'm taking this as a reference. VM phase A reference voltage. Phase A reference voltage VA is equals to VM sine of omega t plus alpha. Omega t plus alpha, where alpha is going to be called as a switching angle. Alpha is going to be called as switching angle. VM sine of omega t plus alpha, so that alpha is going to be called as switching angle. Why we are keeping the switching angle? What is the necessity of keeping the switching angle? Why? What is the reason? What's the reason to keep the switching angle? Yeah, look here. For example, this voltage waveform, it's a sinusoidal one. Just I will draw sinusoidal signal. Irrespective of that alpha and all, I will draw simply one sinusoidal signal. Just have a look. So this is a sinusoidal signal I am showing. Voltage sinusoidal signal. Voltage. Look first. If the fault is occurring at a time t equals to 0 plus, if the fault is occurring at a time t equals to 0 plus, and if this is your sinusoidal signal, like Vm sin omega t, no alpha is taken. No alpha value was taken. So it is simply Vm sin omega t now. No alpha equals 0. Then when the fault is occurring? At the time t equals to 0 plus. So at the time t equals 0 plus, if the fault is occurring, how much is this voltage value? 0 only. That voltage value will be 0. In the sense, if you make that alpha is equals to 0, or if you don't consider this alpha, you are capable to do the fault analysis. Only for 0 voltage input condition. Means at the instant of short circuit fault, source voltage equals to 0. Only for that condition, you are capable to do the fault analysis. I don't know whether you are getting this point or not, what I said. Yeah? Are you getting this point? Please tell me. I am repeating the statement. statement. Please listen. Just we have a sinusoidal signal Vm sin omega t. Fault occurred at time t equals to 0 plus. Right? If you consider the time t equals 0 plus and the sinusoidal signal, means this is the voltage, input voltage value at the instant of fault occurrence. But we don't know at which voltage value the fault is going to occur, right? It may be occurring at 0 voltage instant, or it may be occurring at V maximum instant, or at some voltage like this, or negative V maximum. At any voltage, the fault may occur, right? At any voltage value, the fault may occur. That we don't know. So for a generalization, I am keeping some alpha here, so that even though you keep time t equals 0, it will be Vm sin alpha. Vm sin alpha. If you change that alpha according to the requirement, definitely the instantaneous voltage, source voltage at which the fault is going to occur can be changed. By the way, we are capable to know what is the best condition as well as what is the worst condition. What is the worst condition? Following all of you? Tell me please. Yeah. Good. So I will tell two choices now. I'll tell two choices. One choice, if you take the fault at time t equals to 0, you take alpha. If you take time t equals 0 fault, you take alpha. Okay. Next, if you don't take time t equals to 0, if you take time t naught here, time t naught, you don't consider alpha. You no need to consider alpha. You take the time t naught fault occurrence, you don't consider alpha. That's also okay for me. So by the way, you can write Vm sin omega t naught, right? Vm sin omega t naught, and you can proceed with it. Is it okay? Yeah. So fine. So anyhow, we have taken already fault at time t equals 0 plus, and we are considering that switching angle alpha. Let's continue with this. We apply KVL for this loop at the time t equals to 0 plus condition, or for time t greater than 0 condition. Okay, during short circuit fault. During short circuit fault. So in bracket, you say time t greater than 0. KVL for loop. Phase A loop. Only phase A analysis we are doing. Phase A loop. You have a source voltage VA here. Source voltage VA equals to what? IA into R. Drop in the resistor. IA into R. You can say IF into R also. What correct? IF into R plus but you have this drop L into DIF by dt. L into DIF by dt. Okay, so let's rewrite this by taking this L in this manner. VA by L equals to IF into R by L plus DIF by dt. It's a differential equation. First order differential equation. This you try to write in the generalized form. Something like capital D plus R by L. This we are writing. Capital D plus R by L into IF is equals to VA by L. Capital D plus R by L into IF is equals to VA by L. Like this we can write. This you call as equation number 1, differential equation. Already you know VA here, Vm sin of omega t plus alpha. Vm sin of omega t plus alpha. Now you take the solution of this equation. Solution of equation 1. I'm not going with the complete derivation for the solution. It will consist 2 parts. One is a transient part. Next one is a steady state part. That only we are going to highlight. Okay? Yeah. Solution of equation 1. Solution of equation number 1 will consist or will be like IF is equals to transient component plus steady state component. 2 components here. First component we are naming it as transient component. Next we are calling this as steady state component. Steady state component. Okay. So first I will give the expression for that transient component. See, it is simply like RL circuit AC transient analysis. In the network theory also we can study this. In the network theory also we can study this. So it will be like simply RL circuit, AC transient analysis. So transient component in this, transient component in this one. So ITR is equals to K into e power minus t by tau. Like this. Transient component you are going to get like K into e power minus t by tau, where tau is a time constant of the circuit, L by R, where tau is a time constant of the circuit, which we are naming as L by R. L by R. That's it. Now we will think about that steady state component. We are thinking about that steady state component. Okay. Steady state component we are going to write. First, I will draw the steady state circuit here. Steady state circuit I am going to draw. So it is a resistor. It will be remain same even in transient condition or steady state condition. Voltage source also remains same even in the transient condition as well as steady state condition. Em sin of omega t plus alpha. How you keep the inductor in the steady state? How you keep the inductor in the steady state? How you keep inductor in the steady state? J omega L is a best answer to say. Always, always. If anybody asks you how you represent the inductor in the steady state means you have to keep that as J omega L. J omega L. And as it is AC supply, omega will exist. Omega will exist, so it will have some number. And if it's a DC analysis for you, omega is 0, so J omega L is 0, impedance is 0, it will act as a short circuit. Okay, fine. So I think all of you getting my point. Charan Reddy, are you getting my point? So whatever the current flow in this branch we have, that we are calling as steady state short circuit. Steady state short circuit current, ISS. ISS. Okay. What is the impedance of the network here? R plus J omega L is the impedance of the network. So I have to move with the next slide now. Next slide I'm taking up. Network impedance is R plus J omega L. This you take as mod Z at an angle theta generally. Write this as mod Z at an angle theta, where mod Z is square root of R square plus omega L whole square. Okay, theta is the impedance angle, which is tan inverse of omega L by R. Or you say sometimes X by R. Tan inverse of X by R also we can say. Okay, next. Next thing. See, you know, source voltage VA here, Vm sin of omega t plus alpha. Vm sin of omega t plus alpha. Then how is this steady state current to be expected? How is that steady state current to be expected? That magnitude of peak value of that current will be Vm by mod Z. Peak value of that current will be Vm by mod Z. And you have signal like sin of omega t plus alpha minus theta. Sin of omega t plus alpha minus theta. Okay, so I write here steady state current ISS equals to peak value of this current is Em by mod Z sin signal is omega t plus alpha, and you have minus theta, omega t plus alpha minus theta. It is lagged because it's an inductive network. Inductive network means definitely current is in lagging with respect to supply voltage. Now you write the resultant fault current, so called the DC component plus AC component summation, a transient and steady state components summation, right? So you can say now fault current IF or phase A current is nothing but K into e power minus t by tau transient component steady state Vm by mod Z sin of omega t plus alpha minus theta. Omega t plus alpha minus theta. Yeah. Anywhere, does we mention that means in the derivation? In the derivation, I am asking in the derivation. Anywhere does I mention that fault occurred at time t equals 0? Transient component simply I said k into e power minus t by tau, and we have a steady state component Vm by mod z sin of omega t plus alpha minus theta. Anywhere did I mention that fault is occurring at time t equals 0 in the derivation? In the derivation, no. Means my intention is to tell you. My intention is to tell you. This is a fault current equation or phase of fault current equation, which is valid for the fault occurring at any time. Any time we have a fault. Is it a time t equals 0, time t equals 1 millisecond, time t equals 10 millisecond, 15 millisecond? Any time we have a fault. This is a fault current expression to be taken. Okay, so this fault current equation is valid for fault occurring at any operating time or any time instant. Any time instant. For any time instant, if you have a fault, this equation is valid. Okay. Next. According to the instant of time, this k value is going to be changed. This k value is going to be changed. Of course, same equation I will repeat. I want to rewrite some more thing in this equation itself. IF equals to k into e power minus t by tau plus Vm by mod z sin of omega t plus alpha minus theta. Very simple thing. First one we said already as transient component. Second one we said as a steady state component. First one we said as transient component. Second one we said as steady state component. See, this second signal is obviously a pure sinusoidal signal. Second signal is a pure sinusoidal signal. It is going to be called as AC component of fault current. AC component of fault current, or you can call this as symmetrical component of the fault current. AC component of fault current, else you can name it as symmetrical component of the fault current. Okay, next. This one we are going to call as DC component. DC component of fault current. Or you can name this as DC offset current. DC offset current. DC offset current. Okay. We are naming that as DC offset current. Okay, now we will attempt to get the value of k for the instant of time t equals to 0 fault occurrence. Yeah, I want to give a simple conclusion. Anywhere if you get a doubt, particularly in the RL transient analysis, which fault current I have to take in the calculations? Means you take this current. You take this current only in the fault current calculations. Okay, yeah. Anyway, we will exercise some problems in that computer. So I will try to calculate this k value by taking fault at time t equals to 0. Let's take this equation number. I think 2 it is equation number 2. Yeah, listen. At time t equals to 0 plus fault is occurring, right? At time t equals 0 plus fault is occurring. Just before the fault occurrence. That's the initial condition. Just before the fault occurrence means time t equals to 0 minus. Initial condition means at time t equals to 0 minus, what is the value of fault current? Or what is the value of current circulating in this loop? 0, because we said already it is operating at no load condition. Line is at no load condition, means pre-fault current will not exist at all. That current equals to 0. IF of 0 minus is 0. Now, as we have an inductor in the circuit, even after the fault occurrence, means at the instant of the short circuit fault, IF of 0 plus is nothing but IF of 0 minus initial condition. That value will be automatically comes 0. That value will be 0. Now simply you keep this initial condition in the equation number 2. So equation number 2 at initial conditions will be initial condition. See, if of 0 minus, I'll say, or 0 plus, whatever it is, plus you take 0 plus. K into e power minus t by tau means k into e power minus 0 by tau means e power 0 plus Vm by mod z sine of omega t 0 plus alpha minus theta. Omega t number is 0, na? T number is 0. So it will come like this. And k e power 0 is 1. And fault current is 0 already. So it is k plus Vm by mod z sine of alpha minus theta. Sine of alpha minus theta. And you try to get this k value from this equation. Get this k value minus Vm by mod z sine alpha minus theta. You can minus Vm by mod z sine of alpha minus theta. That's correct, Arvind. It's to create a generic sinusoid. Okay, next. See, I will try to rewrite this k equation by making some assumption. Assuming that this theta is greater compared to alpha. This theta angle is more compared to alpha. Else better, I'll say. Assume that alpha is less than theta, or you can say theta is greater than alpha. Means I want to tell simply this theta minus alpha is positive. Theta minus alpha, that number I am assuming as positive. By making that assumption, this k I am going to call as Vm by mod z sine of theta minus alpha. Means my interest is to push this minus into the sign. If you push this minus into the sign, sine of alpha minus theta rewritten as sine of theta minus alpha. That's k. So now what is a fault current equation or phase current equation here? K Vm by mod z sine theta minus alpha, okay, plus AC current Vm by mod z sine of omega t plus alpha minus theta, na? Plus alpha minus theta, that I will write as minus of theta minus alpha. Because theta minus alpha I assumed as positive, right? Theta minus alpha I assumed as positive. That's why I have rewritten that in the manner of theta minus alpha. Okay, omega t minus an angle we are going to get. Okay. Sorry, sir. I forgot to write that e power minus t by tau. E power minus t by tau plus Vm by mod z sine of omega t minus of theta minus. Now let us draw this exponential. Let's draw the signal. Let's draw the signal in the plot, right? So first signal I will say simply IDC. DC component we have mentioned earlier, IDC. Second one I am going to say simply AC component as IAC. Okay. First I will draw DC component. It will be simply an exponential decay signal. Exponential decay signal. What's the peak of that signal? Vm by mod z sine of theta minus alpha. From that it will start decreasing, and at some time it will reach to 0. Okay. And this AC component, it's a sinusoidal signal with a constant peak. Sinusoidal signal with a constant peak. Those two signals I am going to draw. First, DC component I am going to say. DC component. So it's a IDC and it is time. So we'll have a decrement something like this. And this value was Vm by mod z sine theta minus alpha. That is at time t equals 0. At time t equals 0, you are getting that DC value as Vm by mod z sine of theta minus alpha. And when it is reaching to 0 means at a time 5 times of time constant. At a time 5 times of time constant, the DC signal is reaching to 0. Okay. Next, I want to show that sinusoidal signal. Sinusoidal signal I want to show. Let us show those axes. Current axis I am showing. AC current I have to show, and it's a time axis. Okay. AC current axis, and this was a time axis. Next thing. See, the sinusoidal signal is like Dm by mod z sine of omega t minus some angle. First, I will draw sinusoidal signal. Dm by mod z sine omega t I will draw. Dm by mod z sine omega t I will draw. After drawing that, I will shift that angle. I will shift that sinusoidal signal by an angle of theta minus alpha. So, if you show that sinusoidal signal, may come something like this. Right? So like this, we are going to get that sinusoidal signal. Yeah, so like this, you can get that sinusoidal signal. And this sinusoidal signal having a peak value of Vm by mod z. This sinusoidal signal is having a peak value of Vm by mod z. Okay. So this is Vm by mod z sine omega t. Now the signal I should shift by an angle of theta minus alpha. Na? So I will shift signal shifting the signal by an angle of theta minus alpha. This is that shift I am making for the signal, theta minus alpha shift. Okay, like this you may get. So this blue color signal what I am showing now is that sinusoidal AC signal what we have. Sinusoidal AC signal. So this is Vm by mod z sine of omega t minus of theta minus alpha. Now simply we have to add that exponential signal and this blue color sinusoid. Blue color sinusoid together. Yeah, only blue color sinusoid you have to consider, and then this DC signal. These two we have to add together to get the resultant sinusoid signal. Simple, simple. This blue color sinusoid, which is our steady state component, what is the average value of the signal? What's the average value of the signal? 0. Because pure sine wave means average value will be 0. What is the average value of DC decay component? What is the average value of DC decay component? That will be that number itself. The DC decay component average value will be that DC number itself. But it is changing with respect to time. So simply, if you add the sinusoidal signal to the DC effect, sinusoidal signal to the DC effect, simply the sinusoidal signal will be shifted by the DC effect, I can say. Sinusoidal signal will be shifted by the DC effect. From that time onwards, the average value of the signal is nothing but a DC decay component. Okay, okay. So I will draw that resultant fault current signal now. Is a summation of AC and DC components. Is a fault current IF, IAC plus ADC with respect to time. IAC plus IDC, that's with respect to time, and this is 0, 0. First, let me show the DC decay component. Something like this I am showing. DC decay component. Right. So like this I am showing DC decay component. Next one. See, simply that AC component is added to this now. So AC component is shifted up. So I will show one positive envelope and a negative envelope. Positive envelope and negative envelope, and I will draw that sinusoidal signal in between. Is some positive envelope. I am showing like this. And I am showing negative envelope. And of course, the resultant current will start from 0 only here. Resultant current will start from 0. Okay. So the resultant fault current, summation of AC and DC components, might come something like this. So please kindly adjust with this signal, what I am drawing here. Yeah, so like this will get the submitted sinusoidal. Just draw this signal quickly. This blue color dotted line, DC offset. Okay. Peak value of the signal is Vm by mod Z. Peak value of the signal is Vm by mod Z. And how this waveform is looking for you? Is it a symmetrical waveform or asymmetrical waveform? How this waveform is looking for you? Is it symmetrical or asymmetrical? So please wait for a minute. I will come back. Wait for a minute. I will come back. Meanwhile, you draw this diagram. Yeah. So I have resumed audio, video, and screen. Resumed the audio, video, and screen. Yeah. Kindly go through it. What I am saying you. Yeah. This waveform is asymmetrical. Somebody is saying this waveform is asymmetrical waveform. Means this fault current as a whole, DC plus AC, what you have, it is asymmetrical one. Asymmetrical one. But you know, the DC component is falling down to zero beyond some time, right? The DC component is falling down to zero beyond certain amount of time. That's 5 times of the time constant. If beyond 5 times of time constant, whatever the signal we have here, that I am going to call as steady state component. Steady state component. I am calling as steady state component. Remaining whatever you have means starting from the instant of the short circuit fault to the point of steady state. This whole period we are going to call as transient. In that period again, initial, maybe 1 to 2 cycles. 1 to 2 cycles period, we are going to name it as subtransient. That is number one, period number one. And from this point to the end, means end of this transient, we'll call as transient only. Calling this as transient only. We'll say this is number two. Right? Number one, we are saying subtransient there. Number two, transient, and then we have the steady state. Okay. Why this initial 1 to 2 cycles is going to be called as subtransient? First, I'll say subtransient period in our fault analysis will be 1 to 2 cycles. Okay, whereas transient period, according to this, I am saying 2 to 5 cycles. 2 to 5 cycles, we can say transient, and after that we have the steady state. The question what I asked you earlier, why we are calling this initial period specially as subtransient? I will try to tell the reason. For example, if you take the DC component formula, IDC, what's the formula for DC component? K into e power minus t by tau. That's it. K into e power minus t by tau is a formula for IDC. K into e power minus t by tau. Take the differentiation of the DC component with respect to time. dIDC by dt. Differentiation of this DC component with respect to time. We have K. Differentiation of that e power minus t by tau will be e power minus t by tau only, but you have minus 1 by tau multiplication. E power minus 80 differentiation, e power 80 into a means minus 1 by tau. So this value was minus k by tau into e power minus t by tau. You think about only magnitude of that. See, as time is progressing, maybe from zero. Time is progressing, maybe from zero. This e power minus t by tau value will fall down. E power minus t by tau value will fall down, and finally it will reach to zero at some amount of time. Means the thing what you have to understand here is dIDC by dt, rate of change in the current. It is very, very high, at the instant of fault, maybe at time t equals 0, or very close to the instant of the this dIDC by dt is very, very high. But as time progressing, this rate of change in this DC component is decreasing with respect to time. In that perspective, maybe in the subtransient period means initial period, where the DC decay component, rate of decay in the DC component is very, very high. That period, especially, we are calling as subtransient. Remaining period we are naming as transient. Okay, so what do you mean by subtransient period here? Subtransient period means it is the time period, it is the initial period of fault current, at which rate of decay Rate of decay in DC component is very high. Decay in DC component is very high. Rate of decay in the DC component is very, very high. That is the subtransient period. Okay, yeah. Next thing. See, from this waveform, what we have given, as well as from the equation what we have written, we are going to take up some terms sequentially. First term. What is steady state component here? Steady state peak value Vm by mod z. Steady state peak value was Vm by mod z. What is the RMS value of that? Vrms by mod z. Else you say Vm by mod z whole by root. Okay? Yeah. So first and foremost thing we are going to write is sustained. Number one, I will say. Sustained short circuit current. Short circuit current in bracket RMS value. RMS value. Sustained short circuit current in bracket we are saying RMS value. I'll call this one ISS. Sustained short circuit current ISS, which is Vm by root 2 mod z. Vm by root 2 mod z. That Vm by root 2 we are going to name as Vrms. Of course, it's a per phase voltage you should take in the numerator. Vrms by mod z. RMS voltage per phase value of the system by magnitude of that line impedance. That is a sustained short circuit current. Okay, second one. Listen to the words. Listen to the word what I am saying. What is the initial? What is a initial symmetrical RMS fault current? Initial symmetrical RMS fault current. Initial symmetrical RMS fault. See, initial symmetrical RMS fault current means symmetrical RMS fault current is AC component, right? Symmetrical RMS fault current is nothing but AC component. AC component means this one. What is the RMS value of this AC component signal initially? Initially means near to the instant of the short circuit fault. Near to the instant of short circuit fault means you can say this period. So in this particular period, it will be simple sinusoidal signal only, right? Simple sinusoidal signal. What's the peak value of that sinusoid? Vm by mod z. What's the RMS value of that? Vm by mod z whole by root 2. That's it. Means you have to understand now the initial symmetrical RMS fault current value as well as sustained RMS fault current value, both are exactly okay. So I can say initial symmetrical RMS fault current, nothing but Vm by root 2 mod z, and this is Vrms by mod z now. Vrms by mod z. Clear? Both are same. Both are same. That's the observation in this case. Next thing. Third one. What is the RMS value of asymmetrical component of fault current or asymmetrical fault current? RMS value of asymmetrical fault current. Asymmetrical fault current. RMS value of asymmetrical fault current. See, asymmetrical fault current means it consists of both AC and DC components, right? It consists of both AC and DC components. See, if you have some signal like x plus y sine omega t, if you have one signal f, that is x plus y sine omega t, that x is going to be called as DC component of the signal, y is going to be called as peak value of AC component. Peak value of AC component of the signal. What is the RMS of the signal? What is the RMS value of the signal? Generally, if you have DC and AC components, RMS means you should write square root of RMS value of DC component square plus RMS value of AC component square. So I'll write here square root of RMS of DC component is x only DC component, RMS value, peak value, instantaneous, all are same. Plus RMS of AC component is y by root 2 whole square. Y by root 2 whole square. Okay. So same principle we are going to apply here also to find out that RMS value of the asymmetrical fault current. So I am saying here I asymmetrical is equals to, right, first square root of RMS value of DC component square plus RMS of AC component square. RMS of DC component square plus RMS of AC component square. So simple. RMS of DC component value is nothing but that DC value itself. What is the DC value? What is the DC value? Vm by mod z sine of theta minus alpha into e power minus t by tau. Vm by mod z sine of theta minus alpha into e power minus t by tau. This whole square. Actually, this DC component value is changing with respect to time. So obviously, resultant asymmetrical RMS fault current also changes with respect to time. Okay, fine. What is the RMS of AC component here? Vm by root 2 mod z. Vm by root 2 mod z is whole square. Whole square we can. Okay. So remaining some more terms I am taking up further. Some more terms I am taking up. The first term, next term, what I will take is maximum momentary current. Maximum momentary current. Okay. Or you can call sometimes as making current. In your circuit breaker study, you can say making current. But here I will say simply momentary current. Maximum momentary current. So I'll call this one shortly IMM. See, this maximum momentary current is nothing but highest instantaneous value of fault current at any time. At any time, whatever the highest instantaneous fault current we have, that we are going to name as maximum momentary current. Take the right. Highest instantaneous value of fault. Highest instantaneous value of the fault. See, just have a look here in this diagram. When we are going to get that highest instantaneous value of fault current, when we are going to get that highest value of instantaneous fault current, when? Particularly during subtransient period. So in this particular subtransient period, whatever the peak value of this signal we have, current signal we have, that we are naming as maximum momentary current. The peak signal what we have there, that itself we are going to call as maximum momentary current. Okay, I want to calculate that. Assume that this is happening at a time t naught. That is happening at a time t naught. So I can say IMM, maximum momentary current, is nothing but fault current at a time t naught. Okay, fault current at a time t naught is nothing but DC component at a time t naught plus AC component at a time t naught. DC component at the time t naught plus AC component at the time t naught. Right. Look here. Look here once. See, at this particular time t naught, already you observe that AC component is looking the peak value, right? AC component is already reached to peak value. Means I can say simply at the time t naught, AC component is nothing but Vm by mod z. AC component is nothing but Vm by mod z. But we should calculate the value of DC component at this time t. Okay, so I'll write now. I'll write IAC of T naught from the graph itself. You can call it is Vm by mod z. Vm by mod z. But again, don't ask me why you have not written Vm by mod z sine of omega T naught minus of theta minus alpha. Why? In the sense, from the graph, it is visualized that at the time T naught, maximum value, so called AC component is Vm by mod z. Okay, now we should think about DC component majorly from this point. Think about DC component majorly from this point. Yeah. So I am moving with the next slide to take up that DC component. IDC of T naught, DC component at the time T naught, that is equals to Vm by mod z sin theta minus alpha into e power minus T naught by tau into e power minus T naught by tau. Okay. Now the T naught time is very, very low because the fault occurred very close to zero time. Fault occurred very close to zero time means T naught is very, very low number. If the T naught is very, very low number, e power minus T naught by tau very close to 1. Okay. So as T naught is very, very less, very, very less, you can say e power minus T naught by tau approximately equals to 1. Approximately 1. That's fine. Next, after making that assumption, it will turn to be Vm by mod z sine of theta minus alpha. Vm by mod z sine of theta minus alpha. Let us assume that switching angle alpha equals to 0. Right. Switching angle alpha equals to 0 degree. Now, what will happen to this DC component? Vm by mod z sine theta. You can write it as Vm by mod z sine theta. Vm by mod z sine theta. Okay, and we will assume that X by R ratio of transmission line is very, very high. If X by R ratio of transmission line is very high, theta, that is tan inverse of X by R ratio, that is very close to 90 degree. If theta is very close to 90 degree, sine 90, it's 1, of course. So DC value at time T naught will result into Vm by mod z. Okay, right. I'll say like this. As assume that X by R of line is very high. Line is very high. Very high. So that implies theta very close to 90 degrees. That implies sine theta is approximately 1. Sine theta approximately 1. So therefore, in the next slide, I will say IDC of T naught is approximately equals to Vm by mod z. Please complete this one quickly. Show in the next slide. So IDC of T naught will come approximately Vm by mod z. Therefore, finally, if you take up that maximum momentary current value, AC component Vm by mod z, DC component again Vm by mod z, right? Both are coming as Vm by mod z. So it is double the value of Vm by mod z, you can say. Double the value of Vm by mod z. Sometimes the people will call this as a doubling effect. Sometimes the people will call this as doubling effect. Times of Vm by mod z. And this we are going to rewrite. This we are going to rewrite as 2 into root 2 into Vm by root 2 mod z. 2 into root 2 into Vm by root 2 mod z. What do you mean by Vm by root 2 mod z? What do you mean by Vm by root 2 mod z? What current I should consider the name? What name I should consider for that? Is it sustained short circuit, means steady state short circuit current, or initial symmetrical RMS fault current? Which current you should name it? Which current you should name it? Is it initial current or sustained current? Steady state current. Initial current we have to name. Initial current we have to name. What's the reason? because we are calculating this maximum momentary current near to the fault instant, right? Near to the fault instant. So finally, I can say maximum momentary current value approximately equals to 2 into root 2 into initial symmetrical RMS voltage. Initial symmetrical RMS voltage. So this is the expression for the maximum momentary current. Maximum momentary current. Yeah, okay. So there is one more term called as momentary current RMS value. Momentary current RMS value. So that I will discuss after break. After break, we'll discuss the momentary current RMS value and we will conclude this analysis, right? Yeah. So I have a break for 15 minutes. So I have resumed the audio, video, and screen. Resumed the audio, video, and screen. So let's continue with the momentary current RMS value, what I said just now. That's fifth quantity. Momentary current RMS value. Momentary current. Bracket. I am saying it is RMS. So I'll name it as IM RMS. IM RMS. Very simple definition for this. Very simple definition for this one. It is nothing but asymmetrical RMS fault current only. We have given formula for asymmetrical RMS fault current already. This one. This is the asymmetrical RMS fault current. Now, this value itself is going to be called as momentary current RMS value, particularly in the initial period of the fault occurrence. It will be just after fault occurrence, within very less time. Whatever the asymmetrical RMS fault current we have, that itself we are going to name as momentary current RMS value. Okay, so I can say is the asymmetrical RMS fault current value. RMS fault current value very close to the instant of the short circuit fault. Very close to the instant of short circuit fault. Okay. Next, listen please. See, by making this statement very close to the instant of the short circuit fault, in the sense only this DC component value is going to be changed. Your AC component will be remain same. AC component will be remain same. That is Vm by root 2 mod z whole square RMS value. And whereas in the DC component, very close to the instant of short circuit fault means T is very low time. So e power minus T by tau close to 1. Alpha is assumed as 0. Sin theta is very close to 1. By making those assumptions, this value you can write it as simply Vm by mod z. So it will be Vm by mod z whole square plus Vm by root 2 mod z whole square we can write. Okay, so I can say IM RMS value is the square root of the DC component value we have rewritten as Vm by mod z. And AC component value was Vm by root 2 mod z whole square. Like this, we can write that momentary current RMS value. Momentary current RMS value, or its approximate value. Strictly speaking, it is approximate value because we made those assumptions, right? Alpha is 0, sin theta is close to 1. These are the assumptions we have made. Okay. See, if you rewrite this term, it will be square root of Vm by mod z whole square, you can say first. And it is 1 plus 1 by 2, means it is 3 by 2 now. So Vm by mod z whole square will come out of the square root. So Vm by mod z only. So it will be root 3 by root 2. So Vm by root 2 mod z we are going to call as initial symmetrical RMS fault current. Vm by root 2 mod z is going to be called as initial symmetrical RMS fault current, and this root 3 1.73. Okay, so I can say in the next slide, momentary current RMS value is equals to root 3 into Vm by root 2 mod z is nothing but initial symmetrical RMS fault current. It is 1.732 times of initial symmetrical RMS fault. 1.732 times of initial symmetrical RMS fault. But practically speaking, you don't get this number 1.72. You don't get this number 1.72. It is considered to be 1.6 times. 1.6 times. Okay, so practically this momentary current RMS value will be 1.6 times of initial symmetrical RMS value. Even in the examination also, we should consider to write that momentary current RMS value 1.6 into initial symmetrical RMS fault current in the calculations. Next. What is the maximum value of DC component? Anybody? What is the maximum value of DC component? I think it's number 6. Maximum possible DC component value. Maximum possible DC component value. Yes, how much? How much? dm by mod z. That's what we have taken, right? dm by mod z. By making all those assumptions, you got this current, right? dm by mod z. So I can say IDC maximum possible. See, maximum possible in the sense it may not happen all the time. It may not happen for all the instants of the short circuit faults. Okay, so IDC max value was Vm by mod z. This you can write as Vm by root 2 times of mod z into root, means this value will be root 2 into what is that Vm by root 2 mod z value? That is initial symmetrical RMS fault current. Initial symmetrical RMS fault current. IDC max equals to Vm by root 2 means Vm by root 2 mod z, that will be asymmetrical multiplied with root. Okay, it may not happen all the time. It may not happen all the time. How much is possible value means this value we have to give the answer. But if data is known for you, we have to calculate the DC component value. How much is that maximum? Right. Next. See, I am writing that fault current equation once. Fault occurred at time t equals to 0, right? Fault occurred at time t equals to 0 plus this equation I am writing now. I am repeating, strictly speaking. I am repeating this. Look once. See, this is the fault current equation in the phase A. In the phase A, for the fault at time t equals to 0 plus, right? This is for fault at time t equals to 0 plus fault current, or you can say phase A current. Phase A current. Now I am asking some sequence of questions to you. Sequence of questions. Just answer to me. What is the condition to not have any DC transient from the instant of short circuit fault itself? From the instant of short circuit fault itself, when what is the condition to have no DC transient? In the sense, simply whatever the DC component value we have, that we should make it equals to 0. Make it equal to 0 means sine of theta minus alpha must be equals to 0. Okay, so first condition to not have any DC transient. Condition to not have any DC transient, that is sine of theta minus alpha is equals to 0. Condition to not have any DC transient is sine of theta minus alpha equals 0, means you can write this theta minus alpha equals to 0 degree, or else the switching angle equals to impedance angle of transmission line. You should not write theta equals to alpha. You should not write theta equals to alpha. What you have to write? Switching angle alpha is equals to impedance angle of line. If that is maintained, then don't have any DC transient data. Okay. Second. What is the condition to have maximum positive DC component? What is the condition to have the maximum positive DC component? Condition to have maximum positive DC component. Positive DC component. Maximum positive DC component. In the sense, this Vm by mod z into sine of theta minus alpha, it should be positive number, and that is Vm by mod z. means sine of theta minus alpha should be 1. At the instant of short circuit fault, sine of theta minus alpha should be equals to plus 1. Then only we get plus Vm by mod z. So it is plus 1 means theta minus alpha will be pi by 2, 90 degree. Then what is the angle alpha you can get now? Theta minus pi by 2. Angle alpha will be equals to theta minus pi by 2. Alpha equals to theta minus pi by 2 is a condition for the maximum positive DC component. Now we should take condition for maximum negative DC component now. Condition for maximum negative DC component. Let me write the next slide. Third one. Condition for maximum negative DC component. Negative DC component. So that is sine of theta minus alpha. This value must be equals to minus 1. Sine of theta minus alpha, that value must be equals to minus 1. Means what is it, theta minus alpha? It should be minus 90 degrees. Else you can say alpha is equals to theta plus pi by 2. Alpha is equals to theta plus pi by 2. That is a condition for the maximum negative DC component. One more thing I am stressing here. One more thing. When all these three conditions are valid, condition to not have any DC transient, condition to have maximum positive, condition to have maximum negative DC components. When this is valid, for only the fault occurring at time t equals to 0 plus. If the fault is occurring at a time not equals to 0 plus, at some other time it is occurring, then you can't use these relations what we have written. Because we are writing these relations on the basis of this equation only. This equation is valid only for the fault occurring at time t equals to 0. Okay, I said already, for the fault occurring at any time, may not be time t equals 0 plus, that fault current is nothing but DC component k into e power minus t by tau, k into e power minus t by tau plus AC component Vm by mod z sine of omega t minus of theta minus alpha. Okay, I think all of you getting this one. Okay, so I will take one simple problem now. In that problem, I will try to explain all the things whatever we have discussed till now as a conclusion. Okay, so let's take that problem. There in your PDF file, go through it. See this. Okay, a three-phase transmission line rated for 33 kV, 50 Hz. So three-phase transmission line rated for 33 kV means what is this 33 kV? Line to line RMS voltage rating, 50 Hz frequency. As the series resistance and inductance. Series resistance of the line 3 ohms. Inductance of the line is 30 milliamps. It is assumed that the line is excited by rated voltage with zero source impedance. These are the conditions what I said earlier. Okay, so the line is going to be excited with the rated voltage as well as we don't have any source impedance. Next one. During no load operation, a three-phase short circuit fault occurred at the end of the transmission line at the time t0. Earlier, we have studied the theory topic for the fault occurring at time t equals 0, but now he is saying the fault is occurring at time t0, may not be equals to 0. For this fault, the DC component of phase A, DC component of phase A current is at its maximum positive value at the time t0. We will reread the statement later. Take the reference phase A voltage as V equals to Vm sine of omega t plus 30 degrees. Find the time t0 in milliseconds. In bracket, give the answers in between 0 millisecond and 20 milliseconds. Okay, I will make some more confusion to you. Sine, I am replacing that with cos because we discussed the whole theory with sine, right? But I am going to do the problem with the cosine. I am going to do the problem with cosine. Okay, let's write the data. Data first. E line to line rated 33 kV. That implies what is the B phase value? 33 kV by root 3 RMS per phase voltage 33 kV by root 3. Next, frequency of operation 50 Hz. Transmission line resistance. How much is the resistance of line? 3 ohms. Inductance of transmission line is 30 millihenries. 30 millihenries. Okay. Now, fault is occurring at time t naught. Fault occurs at t equals to t naught time. Next thing. Phase A reference voltage. EA. EM cos of omega t plus 30 degrees. EM cos of omega t plus 30 degrees. Okay, next thing. Just if you want, as it is the first problem, if you want to get some more idea, just you draw the phase A diagram. Okay. Or phase diagram, or you can say phase A diagram. PA is this. This is resistance, inductance, and this is a location of short circuit fault. I will be showing location of short circuit fault. I will be showing, and this is at time t equals to t naught. Fault is getting occurred. Okay. Now RL is in this. See, this is a current I am showing as IA, phase A current. And what is the equation for the phase A current for this fault? What is the equation for that phase A current for this fault? IA equals to a DC component here as well as we have a AC component. DC component as well as AC component. What is DC component? Simply you write K into e power minus t by tau. K into e power minus t by tau. Okay. What is AC component now? AC component means Vm by mod z. Okay. What is the signal? Cosine. Cosine of omega t plus 30 degree minus this impedance angle of the circuit. Okay. Cosine of omega t plus 30 degree minus impedance angle of the circuit, that is theta. So what is the theta angle? Theta angle is tan inverse of omega L by R. So if you take up that tan inverse omega L, how much is that inductance number? 30 millihenry. 30 millihenry by resistance is how much? It is 3. Okay. So get this angle first. How much is that angle? Anybody? Please tell me the angle. 72.3 degrees. 72.3 degrees. We will use it. We will use it. Yeah, 1 minute, please. 1 minute. I will come back. 1 minute. Yeah. See this. See, at the instant of short circuit, this is DC IDC. At the time t equals to t naught plus, DC component value is plus Vm by mod z. That's what he said in the problem, right? phase A, for this fault, the DC component of phase A current is at its maximum positive value. Maximum positive value means IDC of T naught is Vm by mod Z, you should consider. Okay, we have some IAC of T naught, that's okay. But what is the current in the phase A at the instant of short circuit fault? At the instant of the short circuit fault, how much is the fault current value? That will be 0, right? Because it's operating at no load condition before the short circuit fault. Before the fault occurs, he is saying that the line is operating under no load condition. So because of that no load operation, IA of T naught plus will be 0 obviously. Okay, now you dump these terms in this particular equation. So therefore, IA of T naught plus 0 equals to IDC of T naught plus Vm by mod Z. IDC of T naught plus is Vm by mod Z plus Vm by mod Z into cosine omega T naught, which is unknown number now. Omega T naught is unknown number, plus 30 degree minus 72.3 degrees. Okay, so you take this Vm by mod Z to the other side, you'll get minus Vm by mod Z, getting cancelled out. And ultimately, the condition what you can get here is cosine omega T naught plus 30 minus 42 is minus 42. Sorry, minus 42.3 degree is equals to minus 1. Is it okay? That will be equals to minus 1. And cos inverse of minus 1, how much? Cos inverse of minus 1. We have many options here. Many options to write. First option I am saying. First option. We have many options to write. First option I am writing now. Omega T naught minus 42.3 degree is equals to 180 degrees one option. 180 degrees one option. Other option at omega T naught minus 42.3 degree is equals to, at how much angle you will get that minus 1 again? How much angle you will get minus 1 again? Anybody please tell me? How much angle you will get that? What we call minus 1 again. So you'll get 0, minus 90, minus 180 degree is another option. Minus 180 degree is another option. I'm going back. I'm going in the backward, minus 180. Okay, now you take this omega T naught value from the first calculation. 180 plus 42. 180 plus 42 means 222.3 degrees. But this omega T naught generally we keep in radian. Omega T naught generally we keep in radian. You keep this in radian by multiplying pi by 180. Okay. Now the time T naught is nothing but 222.3 degree into pi by 180 by omega 2 pi into frequency, that is 50. 2 pi into frequency, that is 50. You please calculate time from this one. Next, you can write here minus 180 plus 42. Minus 180 plus 42 means it is 138 minus 137.7 degree. And you calculate the time P naught from this. It is multiplied in pi by 180. So it is negative time, negative value. So negative time should not be our answer. We have to give a positive time. Not only that, the time should be in the range of 0 to 20 milliseconds, as he said in the problem. We have to give the time in the range of 0 to 20 milliseconds. Yeah, you please calculate the P naught from the first one. I will come back within 1 minute, please. I'll come back within 1 minute. Please calculate this time T naught. So you are getting 12.35 milliseconds. You are getting this T naught 12.35 milliseconds. That's it. So if the fault occurs at a time t equals to 12.35 milliseconds, the phase A component is going to see maximum positive value. Okay, same question. Same question. Same as previous question. So what is the time t naught? What is the time t naught for which no DC transient occurs? No DC transient occurs in phase A current. Occurs in phase A current. Yeah, what you have to do for this? Tell me please. What you have to do for this? What is the time t naught for which no DC transient occurs for the phase A current? Simple, simple. See, let's move to previous slide. So I am taking up this equation now, and your DC component value should be equals to 0 at the instant of short circuit fault. So this number will keep 0 simply. Of course, IA current will be 0. IA current will be 0, and you can say cos of omega t naught plus 30 minus theta, this value must be equals to 0. That's the condition. Okay, so I can say for this, IDC of t naught value must be equals to 0. Therefore, cosine of omega t naught plus 30 degree minus theta must be equals to 0 from the equation. From the current equation, you should say. I of t naught plus is also equals to 0. Now, I can get again two options here. Two options. First option will be omega t naught plus 30 degree minus theta means minus 72.3 degree is equals to, when we will meet that cosine value 0, at 90 degree you will meet. What's the another option? What's the other option? Omega t naught plus 30 degree minus 72.3 degree at how much time we will get 0 again. So 90 plus 180 means it will be 270 degrees. 270 degree again you will meet 0. Okay, getting this one? Getting? Yeah, we calculate this time now. What is omega t naught from this? It is 90 minus 30 plus 72.3 degree. Calculate the triangle, how much? And here also, omega t naught value, if you calculate 270 plus 72.3 degree minus 30 degrees. Okay, 90 minus 30 means 60. 60 plus 72. 60 plus 72. How much you can get? 122, I think. 132. 132.3. So from the first one, time t naught will be equals to 132.3 degree into pi by 180 by omega 2 pi into 50. Whereas for the second one, the time t naught is equals to 270 plus 180, it will be simply plus 180 means 200, 280, 312. 312.3 degree into pi by 180 by 2 pi into 50. Calculate the times. Times 2 times you will get now. Two values of t naught. First number 7.35 milliseconds. 7.35 milliseconds. I think second one 17.35 milliseconds. 17.35 milliseconds. Okay. So according to that range, definitely they will mention in the option. They will mention in the option that you need to give the answer in between 0 to 10 milliseconds or 10 to 20 milliseconds. They will give in the option. According to that, you have to type that answer in the blank. Getting me, all of you? All of you getting this one? Now, next thing. See, till now, we discussed about phase A fault current only. Phase A fault current. What about the fault current in phase B? What about the fault current in phase C? How these two currents will be? That we have to discuss. Only little I will discuss. Okay, yeah. So I'll take in the next slide. Else, rather than going for those currents here itself, let's do some more extension to this. Let's do some more extension to this. Thereafter, I'll think about that B and C currents. Let's do some extension. Find number one. Previous problem, same as previous problem. Take the data from previous problem. Data of previous problem. Okay. So first I am asking you, find maximum possible DC component. Maximum possible DC component. DC component. Second one, find momentary current RMS. Momentary current RMS. Next one, find maximum momentary current. Maximum momentary current. Okay. Last one I am saying, find initial symmetrical RMS fault current. Initial symmetrical RMS fault current. RMS fault current. Yeah. Please take up these calculations quickly. Please kindly take up these calculations quickly. Minus 90 also you can take if you want, Vinitha. That's your wish. Whichever the angle is making equal to that, you can take. Yeah. So let's take the first one here. First one in the solution. First one in the solution. What is the maximum possible DC component value? IDC max. What's the formula for IDC max? Root 2 into initial symmetrical RMS fault current. Root 2 into initial symmetrical RMS fault current. Okay. This is nothing but root 2 into. Okay. I will calculate initial symmetrical RMS fault current first, then I will go for that IDC max. See, initial symmetrical RMS fault current formula Vm by root 2 times of mod Z. Vm by root 2 times of mod Z. That Vm by root 2 is the value Vrms, and in the denominator we have mod Z. Okay. What is Vrms value? 33 kV by root 3. 33 kV by root 3. I have given in the data, right? This one. 33 kV by root 3 is a Vrms per phase. And you have to calculate mod Z value from this resistance and inductance values. Okay. So, where Vrms per phase number 33 by root 3 in kilowatts. Okay. And mod Z value, it is square root of R square plus omega L whole square. Okay. So resistance value, I think 3 ohms given in the data. Omega L, 2 pi into 50. Inductance value, I think 30 millihenry. 30 millihenry whole square. R square plus omega L square under. Yeah, you please calculate this mod Z value. Anybody please tell me that number. R square plus omega L whole square or R square plus X square number. 9.88 ohms. 9.88 ohms. This you substitute into that symmetrical RMS fault current value. So you can get initial symmetrical RMS fault current as 33 by root 3 by you have 9.88. It will be in kiloamps. How much is this number? How much is that number? How much? So it will be 1.926 kiloamps. 1.926 kiloamps. That's the initial symmetrical RMS fault current. And what's the DC current maximum value? DC current maximum value is root 2 into 1.926 kA. Root 2 into 1.926 kiloamps. How much is this number? 2.724 kiloamperes. That is a DC max, IDC max. 2.724 kiloamperes. Okay. What's the second one? What is the second one I am asking you? Second one. Momentary current RMS. What is the formula for the momentary current RMS? It is nothing but 1.6 times of initial symmetrical RMS fault current. 1.6 times of initial symmetrical RMS fault current. Nothing but 1.6 into initial symmetrical RMS fault current is 1.96 K. How much is this number? 1.6 into this number. 3.0816. 3.0816 kiloamperes is a momentary current RMS value. Momentary current RMS value. Next, third one. Maximum momentary current is asking. IMN. Maximum momentary current. What's the formula for maximum momentary current? 2 into root 2 into initial symmetrical RMS fault current. 2 into root 2 into initial symmetrical RMS fault current. So it is 2 into root 2 into 1.926. 1.926. How much is this number? How much is this number? Yeah, tell me please. 2 into root 2 into 1.926. Anybody? This value was 5.447 kiloamperes. 5.447 kiloamperes. What's the last one he is asking? Last one, it's a initial symmetrical RMS fault current only. That will be 1.926 kiloamperes. Already we have calculated. Initial symmetrical RMS fault current is 1.926 kiloamperes. 1.926 kiloamperes. Yeah. That's it. Okay. Now we are thinking about remaining phases currents also. B and C currents. B and C currents. Very simple to understand actually. So I'm moving to the next slide. Just have a look here. So this is a phase A voltage, Vm sin of omega t plus alpha, phase A voltage. Phase B voltage, Vm sin of omega t plus alpha minus 120 degrees. Phase C voltage, Vm sin of omega t plus alpha plus 120 degrees. Like this way. Okay, phase A voltage, Vm sin of omega t plus alpha. Phase B, Vm sin of omega t plus alpha minus 120. Next one is Vm sin of omega t plus alpha plus 120 degree. These are the phase voltages. What is a phase A fault current now? During short circuit, what is the phase A fault current? Some constant K into e power minus t by tau plus Vm by mod z sin of omega t plus alpha minus theta. Simple equation. DC component is K into e power minus t by tau plus AC component is Vm by mod z sin of omega t plus alpha minus theta. Okay, what is the B current now? Phase B current. Some constant K into e power minus t by tau plus Vm by mod z sin of omega t plus alpha minus 120 degree is a whole angle of VB minus theta we should minus theta. And phase C current will be K into e power minus t by tau plus Vm by mod z sin of, you get now omega t plus alpha plus 120 degree minus theta. Plus 120 degree minus theta we have to come. Okay, but these constants are different. From one phase to other phase, these constants are different. First constant you get K1, second constant K2, third constant you get as K3. K1, K2, K3. These are the constants what we can get in the phase A, phase B, phase C currents. Means my interest is to tell you AC component in the three phases will be having equal magnitude. AC component value in the three phases will be having equal magnitudes. But DC component magnitudes are different from one phase to other phase. DC component magnitudes are different from one phase to other phase. That's something you have to observe. For example, you get a fault at time t equals 0. If you have fault at time t equals 0, I am writing for fault at time t equals 0. Fault at time t equals to 0 plus. What is K1 number? Means that's a phase A DC component constant value K1. We have done this already, right? Pm by mod z sine of theta minus alpha. Okay, what is K2? Guess the K2 value. Guess the K2. Simply in place of alpha, you replace alpha minus 120 degree. Simply in place of alpha, you keep alpha minus 120. So it's Vm by mod z sine of theta minus alpha plus 120. What is K3? Constant. Vm by mod z sine of theta minus alpha minus 120 degree. Like this, you will get these constants K1, K2, K3 for the fault at the time t equals to 0. Getting. So all the three phases might have equal AC component value in magnitude, but different values of DC components in the three phases will be experienced. Okay, so I will write that statement. I will write that statement here. So during this symmetrical fault or three-phase fault, AC component magnitude value, AC component magnitude in all three phases is equal. Whereas DC component value was different in the three phases. Different in three phases. Okay. AC component value will be equal, but DC component value will be different in the three phases. This observation we should have. See, by this point we completed that short circuit on the no load operating transmission line. Now we will go into the next topic, that is three-phase short circuit on the no load operating alternator. Three-phase short circuit on no load operating alternator. I am moving to the next slide to take up the next topic. So that is three-phase short circuit fault. Three-phase short circuit fault on no load operating alternator. This is a bit confusing, of course, a bit difficult also to understand, but still I will try to make it a bit easy. Yeah. Listen, please. Listen, all of you. So I'm showing one alternator just as a symbol to you, like this. It's a generator, three-phase generator. So three wires are coming out like this. There are ABC three wires. ABC three wires. Next. Generally, this alternator will have some synchronous reactance, right? This alternator will have some synchronous reactance, which will have two components. One is leakage, next one is the armature reaction component. Okay, first I will write that statement. Synchronous reactance of alternator XS, XL plus XA. XL, it's a leakage resistance of alternator, stator, sorry, reactance. leakage reactance of alternating stator. And this is armature reaction reactance. Armature reaction reactance. Depends upon the armature reaction value. Armature reaction in the sense, effect of armature flux on the main field flux. Okay, next. See, for example, we had a three-phase short circuit fault on the alternating terminals. At some time, maybe time t equals to 0. And we waited for a long amount of time. All the transients, subtransients has gone away. We entered into steady state, you assume first. We entered into steady state. After reaching to steady state, the per phase model of alternator, how it will be? Means we have a generator EMF EG with this excess reactance, XL plus XA. That's it. Okay, yeah, I'll write this. Per phase equivalent circuit of alternator. Per phase circuit of alternator under steady state. What occurred and we reach into steady state. In that steady state, I am drawing this one. So this is that per phase EMF, induced EMF EG. So I am showing here two reactances. One is leakage reactance value XL, and the next one we are showing as armature reaction reactance as XA. This is a neutral per phase model. Okay, and this is the location of short circuit which we have shown earlier. And this combination of this XL and XA we have called as XS. Next. Yeah, I think nobody is having a doubt till this point. Till this point, nobody is having a doubt. Yeah, listen. See, before occurrence of short circuit fault, see, in the air gap, we have only rotor flux. Yeah, if it is a machine's topic, you are feeling, you don't listen to this anonymous attendee. If you feel it's a machine's topic, please don't listen. Yeah. We have only rotor flux in the air gap under no load operation. Because you don't have any armature current, right? So we don't have any armature flux at all. We have only main field flux, or you can say rotor flux. Okay, yeah. I am showing one plot here. View. Simple plot. Y-axis and the x-axis. And this is a flux, air gap flux, resultant, of course. Resultant air gap flux. And this is with respect to time I am talking. That is with respect to time. The resistance we are neglecting, Gyaneswari. We are neglecting the resistance. Look here. This is the instant of time at which we are going to get the fault. Just before fault occurs, we don't have any armature flux at all. We have only rotor flux in the air gap. I am showing that flux something like this. It was only rotor flux in the air gap. Okay, now next. See, from the instant of the short circuit fault, armature will start carrying the current. Whenever this armature starts carrying the current, definitely some armature flux is getting created in the air gap. That armature flux will show its effect on the main field flux. Okay, so whenever it is showing its effect on the main field flux, how is the resultant flux in the air gap to be expected? It may be decreasing. Continuously. Because what is the nature of current flow in the stator? Lagging current, right? Because of pure reactive nature of network, we have a lagging current. Lagging current means we have a demagnetizing action of armature reaction. If you have a demagnetizing action of armature reaction, Resultant flux in the area will decrease continuously and finally reaches to some steady state value. This is a thing you have to understand now. If you want, I will write that also in the next slide. Before fault occurrence, air gap flux will be only rotor flux. Air gap flux will be only rotor flux. Rotor flux. Next, from the instant of short circuit, armature current rising up, armature current increases. Better, it may confuse you later. From the instant of short circuit, armature flux created in the air gap, and resultant flux in the air gap starts decreasing. Resultant flux in the air gap starts decreasing. And finally reaches to some steady state level. Okay. Are you clear about this statement, what I have written? See, whatever the armature flux getting created at the instant of short circuit fault, it may not penetrate into the air gap as easy. According to constant flux linkages theorem, the flux linkage value will not change instantaneously. Flux linking with a winding will not change instantaneously. By that way, just before fault occurrence, just after fault occurrence, resultant flux linkages will be remains same. But as time progresses, the flux linkage or flux value starts decreasing. But it won't decrease to the steady state value all of a sudden. It won't decrease to the steady state value all of a sudden. It will start decreasing and finally reaches to some steady state number we are seeing. Okay, yeah. So if you want, you write that statement also. No instantaneous change. No instantaneous change in the air gap flux due to constant flux linkages theorem. So now what I can say is, from this point onwards, the flux starts decreasing like this. Okay, and it may come down inside, and finally it will reach to some steady state value. Okay, so I can say this is the point at which we have reached the steady state. Yeah, so I think all of you getting this one. Resistance is neglected. I said many times. Resistance is neglected. Yeah, fine. Next thing. Listen. See, this fall period, this flux fall period, I am dividing into three parts. Okay, before saying that as a three parts, first I will call this one steady state flux. Steady state flux phi SS. Steady state flux, it is phi SS. Okay. Next, I will discuss one very simple topic. Very simple topic. Maybe flux linkage, flux linkages with respect to flux linkages. Try to understand that topic first. After that, I will try to interlink that to our alternator, what we are studying. Look here, look here. For example, completely a different study from our view. This is one conducting ring we have. This one conducting ring. Conducting ring. Conducting ring. Now, on this conducting ring, all of a sudden, I am ejecting a DC flux. DC. I am ejecting some DC flux on this. So maybe that DC flux is going in this particular direction on this conducting ring. Suddenly, this DC flux was attacked on this ring. All of you know that whenever this DC flux is attacked onto the conducting ring, suddenly the conducting ring will experience a rate of change in the flux. Suddenly, the conducting ring will experience a rate of change in the flux. Because of that, definitely some EMF is going to be induced in the conducting ring. EMF is going to be induced in the conducting ring, and definitely because of that EMF, as it is a closed one, it is going to carry some current. That current may flow in this particular direction. In this particular direction, it's going to carry some current. But you see, in the steady state, if you think steady state, whenever some DC flux is attacking on some conductor, whenever DC flux is ejecting on a conductor steady state, obviously the conductor will not experience any rate of change in the flux. So obviously induced EMF will be zero, I will say. In the steady state, it is zero. But in the transient time, at the instant of attack, definitely this DC flux will cause to a transient EMF induced in the conducting. Okay, E is a transient EMF. Transient EMF induced in the conducting ring. Because of that transient EMF, some current will circulate in this ring. How is that current value? How is that current? That we are going to take up now. For example, if I take y-axis and x-axis, something like this, and it's a current in the ring, and this is with respect to time. For example, if this ring is having zero resistance, listen here. If this ring is having zero resistance means that this current will not decrease. And it will continue to be the constant number. Okay. So if the ring is having zero resistance, this current will be constant value like this. For resistance value 0 for the ring. But practically speaking, this ring definitely have some resistance value. Because of that, whatever the energy we have, energy stored in the ring by means of magnetic form, that will be dissipated in the resistor, and the current value will exponentially decays and finally reaches to 0. So I can say that this current may start decrease like this and finally reaches to 0. If that resistance is not equals to 0, which is a practical case for you? Is it resistance 0 or non-zero? Which is a practical case for you? Which is a practical case? Exponential decreasing. Non-zero resistance is a more practical case for us. Means simply from this point onwards, what you have to understand is very simple. We have a conducting ring or a closed conducting body. Onto that conducting body, if you put one DC flux, at the instant when the DC flux touches the conducting body, touches the conducting body experiences rate of change in the flux. EMF will be induced in the transient time. Because of that, current will be circulated. But as time progresses, the current will start decrease exponentially and finally reaches to 0. Okay, if it's a AC flux for you, you know that current will circulate with respect to time as a sinusoid. If it's a AC, that we are not discussing. All of you clear about this concept? All of you clear about this concept? Tell me, please. If you. Okay, fine. Next, let's move. Let's move to the alternator now. Let's move to the actual study alternator. This is a stator of our alternator. It is a stator of our alternator. I'll show like this. Yeah. Next thing. I'll show rotor also here. Rotor also. Just observe. Yeah. And so this is a field winding of the rotor. Already it is excited with the DC supply. Excited with DC supply. On the rotor pole phase, we will have some damper bars. I'm showing those damper bars here, like this. These damper bars also closed ones. These damper bars also closed ones. Okay, next thing. See, this rotor body is rotating in certain direction with synchronous speed. Rotor body is rotating in this direction with the synchronous speed, ns. Synchronous. Now, see, we have some stator winding in the stator frame. I'm not showing it, but I will show 3 wires ABC of the stator. 3 wires ABC of the stator, something like this. Next thing. ILYR time constant. Next thing. Listen, please. Listen. No fault. No fault, nothing. Only rotor is rotating in the air gap. Along with the rotor, rotor flux is also rotating, right? Along with the rotor flux is also rotating. Yes or no? Because it's a DC flux. Okay. See, whenever the short circuit occurred on the alternator, all the 3 wires will carry their own currents. Whenever all the 3 wires are carrying their own currents, definitely it will create a rotating magnetic field in the air gap. Tell me please. Whenever I need your response at this point, each and every step you have to learn and you have to understand. That's the thing. Short circuit fault occurred. 3 wires are carrying current. There is a rotating magnetic field set up in the air gap. Yes. In which direction that rotating magnetic field will rotate? In the same direction of rotor. In the same direction of rotor, that rotating magnetic field will be rotating. So this is the stator rotating magnetic field created. Stator rotating magnetic field created. Now, as a person, listen to me. Listen. As a person, we are standing on the rotor, let us say. We are sitting on the rotor. No fault. We are sitting on the rotor and rotor is continuously rotating. Okay. All of a sudden, fault occurred. A rotating magnetic field was created in the air gap. How is that rotating magnetic field with respect to you? Is it static or rotating? With respect to rotor, how is it static? Or you can say constant. Means, can I feel that by sitting on the rotor, just after the fault has been occurred, suddenly some DC flux has attacked on me. Just by sitting on the rotor, just after fault occurrence, can I feel that a DC flux has attacked on me? Means attacked on the field winding, attacked on the damper bars. Yes or no? Yes. Yes, right? Because of that DC flux attack, definitely there will be some EMF induced in the damper bars as well as some EMF induced in the field winding also. Transient EMFs will be induced in the damper bars in the field winding. These transient EMFs will circulate some transient currents. These transient currents will produce some transient fluxes. Field winding transient flux, damper winding transient flux. Okay, these fluxes will oppose the stator flux, will oppose the armature flux, or you can say stator flux. By that way, it will make the resultant flux in the air gap remains constant at the instant of the short circuit. Some of you may be confused. I said many things at this spot. Let me write each and every one. See this. At the instant of short circuit fault, stator or armature stator rotating magnetic field created, and it attacks on rotor, but it looks to be stationary with respect to rotor. It looks to be stationary with respect to rotor. At the instant, yeah, you please complete this one. I am writing each and every statement. Try to understand. Hema and Tulasi. At the instant, that's stationary. At the instant of stator RMF attack on rotor, a transient EMF will be induced in field winding and damper winding. Okay, that implies some transient currents and transient fluxes will be created in the air gap, which opposes the stator flux, or you can say armature flux. It opposes the armature flux. Armature flux in bracket to satisfy constant flux linkages theorem. Satisfy constant flux linkages theorem. Satisfy the constant flux linkages. Okay, now I will write those transient fluxes created. One is a field winding transient flux. Next one is a damper winding transient flux. I'll show you in the next slide. Pi FT, it is a field winding transient flux. Pi DWT word I am using. This is damper winding transient flux. damper winding transient flux. But these two fluxes are exponential decay. Phi ft and phi dwt, these are decaying exponentially decaying fluxes. Exponentially decaying fluxes. So I'm showing previous slide. Somebody is still writing. Please complete it quickly. Okay. So now the resultant flux in the air gap at the instant of short circuit fault, will be remain same, phi rotor only, but the same phi rotor what here that I am writing as ISS, so-called steady state flux, plus field winding transient flux, plus damper winding transient flux. ISS plus phi ft, field winding transient flux, plus damper winding transient flux. And this resultant is nothing but the rotor flux only. Resultant is nothing but the rotor flux only. Okay, right. But as time progressing, these fluxes are decreasing, right? Decreasing. Which flux will reach to zero first? Which flux will reach to zero first? Zero. Whichever the winding, damper or field, whatever, whichever the winding having low expiry ratio or low time constant, that flux will reach to zero first. So generally, damper bars will have high resistance, low inductance. Okay, so generally L by R of means time constant of damper bars will be less compared to L by R of field winding. So in the view of this, that implies phi dwt reaches to zero quickly. But definitely after some time, phi ft also reaches to zero. Yeah, one should not confuse between the field winding flux and field winding transient flux. Actually, you see this diagram, we have a DC supply here, right? Because of this DC supply, we have a rotor flux. Means we have a field flux. Along with that field flux, there is some transient flux created by the field winding because of the induced EMF. Okay, so what are the fluxes we have in the area? A rotor flux we have one thing, field winding transient flux we have one thing. Okay, and then we have that a damper winding transient flux we have, and then stator flux. The stator flux is in opposite direction to all these three summation. All of you getting this? Okay, yeah. Now we are saying within very less amount of time, maybe up to this point itself, by this point itself, I am saying that damper winding transient flux was reached to zero. So beyond this point, we have only steady state flux and field winding transient flux, and beyond some time, field winding transient flux also becomes zero, and we have only steady state. Okay, so I am calling this period as a subtransient period, number one, and this period as a transient period, naming as number two. First period is subtransient, and second period we are showing as we call transient period. Okay, now tell me please. From the instant of short circuit fault, I will write this statement. From the instant of short circuit, What is happening to resultant flux in the air gap? What is happening to resultant flux in the air gap? Decreasing or increasing? Resultant flux in the air gap decreasing. Okay. What is how is the armature reaction? How is the armature reaction? Armature reaction increasing or decreasing? Armature reaction, is it increasing or decreasing? Armature reaction is increasing, right? Why you are saying again decreasing? Armature reaction is increasing. Why? In the sense, armature flux is showing its effect continuously on the main field flux, and the resultant flux in the air gap is decreasing. Means armature flux effect on the main field flux is increasing, right? By that way, only resultant flux is coming down. Armature reaction is increasing. Tell me please, if armature reaction is increasing, how is the armature reaction reactance? Armature reaction reactance value also increases. Armature reaction reactance also increases. If armature reaction reactance is increasing, how is the net reactance of machine also increasing with respect to time? So at the instant of short circuit, we have a very low reactance for the machine. Very low reactance for the machine. But as time progressing from the instant of short circuit, reactance of machine starts increasing. And finally it will reach to a number like XL plus XA in the steady state. XL plus XA in the steady state. All of you getting my words? Yeah. Okay, we will stop at this point. Tomorrow I will continue with this one. But what I'll do tomorrow is directly I will take subtransient period. Where the armature reaction is very low. Then next I will move to transient period, little increase in armature reaction, then steady state. Okay, how are those reactants that I am going to write? And then we will show that fault current waveform, and then whatever the terms we studied in the RL circuit, that I will repeat. We'll do on top. It is very important topic in the view of GATE examination. This topic what we are discussing is very important. By this way only, we are going to learn some more things which will clear many doubts. In the power system analysis. So class was completed. If you have any doubts, come to live. Don't ask me in Q&A. Please kindly don't ask me in Q&A. Please come to live. Talk with me. I don't give answers to you in the Q&A. Please come live. Please raise your hands. Prithviraj.
Hello, sir.
Tell me, Prithviraj.
Sir, at this instant, phi resultant is reducing, sir. Okay, sir. Armature reaction
from the instant of short circuit. From the instant of short circuit.
Okay, sir. From the instant of short circuit.
As we progress further.
Okay, sir. Armature reaction another perugutundi, dani valla XA perugutundi kada sir.
Yes.
Dani valla XS kuda perugutundi overall ga.
Yes.
So current anadi taggali kada sir.
Tagutundi. That I will show tomorrow.
Current taggడం వల్ల మళ్ళీ armature reaction అంటే తగ్గుతుంది కదా sir?
No. The current decrement is because of that phi FP, phi DW decrement.
Sir.
Field winding transient flux and damper winding transient flux are decreasing, right?
Yes, sir.
Because of that, armature reaction is increasing, you feel?
No, sir. I am saying that excess increase అవుతుంది కదా sir armature reaction వల్ల. Excess పెరిగినప్పుడు కరెంట్ అనేది తగ్గుతుంది కదా సార్ సర్క్యూట్ లో.
Armature current will decrease definitely. Armature current will decrease.
దాని వల్ల లూప్ లో ఆర్మేచర్ రియాక్షన్ మళ్ళీ తగ్గుతుంది కదా సార్ అని అడుగుతున్నాను.
No. It's not in that way. If you listen tomorrow class, you will get clarity about it.
Okay, sir. Sir, one more doubt is at the starting of the class, assumptions in fault analysis you said first point na sir. Sir first point అర్థం కాలేదు సార్ అదొకటి చెప్తారా?
XD double dash is the reactance what we are going to discuss now, because many of the times we have to take up the subtransient reactance only, subtransient fault current calculation.
Okay sir.
We are doing subtransient fault current calculation, we should take only subtransient reactance in the network.
Okay sir.
Why that subtransient EMF comes means, particularly if the pre-fault system is a loaded one.
Okay sir.
Before occurrence of fault, if the system is a loaded one, we need to consider the pre-fault current also into fault analysis.
Okay sir.
To consider that one, we are keeping that EG double dash.
Okay sir.
Okay. So
Okay,
anyhow, till now we are discussing about no load analysis only.
Yes sir.
Once after we complete this alternator and all, I will discuss about the loaded analysis also.
Okay sir.
There we will see how to calculate the EG double dash and all.
Okay sir.
Okay.
Sir,
simple,
okay, sir.
simple remembrance. EG double dash I am keeping in order to take care of the pre-fault current also into fault analysis.
Okay sir. Sir, one more doubt is RMS value of asymmetrical fault current. Sir, RMS of DC component ఏమవుతుంది సార్ మామూలుగా? అంటే యావరేజ్ కాంపోనెంట్స్ అన్ని మాక్సిమం కదా సార్?
DC value itself, that's it. That equation what you have, that itself is RMS.
సార్ అంటే నా ఉద్దేశం ఏంటంటే ఇప్పుడు విఎం బై అది ఒకసారి ఓపెన్ చేయగలరా సార్ స్లైడ్, ఆర్ఎంఎస్ వాల్యూ ఆఫ్ అసిమెట్రికల్ ఫాల్ట్. సార్ ఇప్పుడు దీనికి డిసి కాంపోనెంట్ కి యావరేజ్ వాల్యూ అంటే మనం విఎం బై మాడ్ జెడ్ సైన్ థీటా మైనస్ ఆల్ఫా అని రాస్తాం సార్. ఈ మైనస్ టీ బై టౌ కూడా ఇంక్లూడ్ చేయాలా యావరేజ్ వాల్యూ?
DC component is varying with respect to time, right?
Yes sir, yes sir.
Then obviously RMS of DC component is varying with respect to time.
ఓకే సార్. ఓన్లీ మాక్సిమం వాల్యూ వచ్చినప్పుడు మాత్రమే మనం టైం ఈ మైనస్ టీ బై టౌ అనేది తీసేస్తాం, అంతే కదా సార్?
Why you are removing it? We are assuming that is 1.
Okay sir, okay sir. At that
this is not 1 here, right?
Yes sir, yes sir.
We have taken that as 1 while we are calculating momentary current.
Momentary current, yes sir.
Okay.
And sir for fault at t is equal to 0 plus అని చెప్పారు కదా సార్, కండిషన్స్ అనుకున్నాం కదా సార్. సార్ ఈ t is equal to 0 plus కి t is equal to at some other time కి నాకు డిఫరెన్షియేషన్ అర్థం కావట్లేదు సార్.
What you want to understand from this? You want to know these conditions?
సార్ సార్ గ్రాఫ్ ఉంది కదా సార్ మనది,
these conditions
దిస్ కండిషన్ అంటే t is equal to 0 plus కి t is equal to some other time కి డిఫరెన్షియేషన్ ఏముంది సార్ యాక్చువల్ గా?
See,
గ్రాఫ్
1 minute. So your fault current or phase A current is k into e power minus t by tau.
Okay sir.
Plus Em by mod z sin of omega minus of theta minus
alpha. Yes sir.
So this is the fault current equation for the fault at any time.
Yes sir.
Okay. So fault at t naught time.
Okay sir.
T naught time. And IA of t naught plus is 0.
Yes sir.
This one. Case 1.
Okay sir, no load condition కాబట్టి
IDC of t naught plus is equals to 0. Means no DC transient.
Okay sir.
No DC transient. Okay, in this case of no DC transient,
okay.
IA of t naught plus is 0 and DC component value is also 0. Plus what you get now?
Sin of omega t minus theta minus alpha is equal to
Em by mod z sin of
omega t
naught minus of theta minus alpha.
Okay sir.
If that is 0, you should say sin of omega t naught minus of theta minus alpha
equal to
0.
Yes sir.
Then from this you can get the time t naught at which you are going to get it.
Okay sir.
How much is the t naught? If it is 0, you can send this to the other side, theta minus alpha by omega.
అంటే సార్ ఇప్పుడు మనం టీ నాట్ అన్నది విత్ రెస్పెక్ట్ టు న్యాచురల్ సప్లై వోల్టేజ్ బట్టి చూస్తున్నాం సార్.
No, actually we don't know at what supply voltage we are going to get the fault. You should be ready. You should be ready to take the fault current value at any instant of short circuit. Right?
జీరో ఇన్స్టంట్ కి అంటే జీరో ఇన్స్టంట్ అంటే ఏంటంటే natural voltage zero instant సార్ దాని అర్థం?
No. Time t equals 0 means the time t equals 0, we have dumped into voltage equation. And if you check what is that instantaneous voltage.
Oh, okay, sir.
But if you don't take alpha, what I said you earlier, if you don't take alpha, you will get that instantaneous value as 0 only, right?
Yes, sir. Yes, sir.
Then you are doing fault analysis only for one condition. You are not generalizing it.
Okay, sir.
To generalize that one, you take alpha. If you are not interested to take alpha, don't say that fault is at time t equals 0. Say at some time t naught.
Okay, sir.
So here I have taken t naught as well as alpha, both. Any one is sufficient to me.
Okay, sir.
Okay.
Okay, sir. Okay.
Any other doubt you have?
That's it, sir.
Yeah.
Thanks.
Pranjali.
Hello, sir.
Tell me, Pranjali.
Sir, on page number 36.
Okay.
Sir, in this graph, this first cycle is maximum momentary current IMM. And what is this peak Vm by mod Z? For which cycle this is Vm by mod Z?
Oh, whatever it may be, already we reached the peak value here. Means from this point to this point, if you see, that is Vm by mod Z only, right?
Yes, sir. Because it is double, 2 times Vm by mod Z.
Not double. Why you are saying double?
Sir, we got that 2 Vm by mod Z.
We got it. Okay, you keep it aside. What's your doubt?
Sir, this at the end we have written this Vm by mod Z.
That's okay. That's okay. You leave it. What's your doubt?
Sir, my doubt is that for which cycle this is Vm by mod Z.
Listen. Just I have seen this waveform.
Yes.
After seeing the waveform, how much is the highest instantaneous current? I have identified that here. Means at the time t naught, I have to measure this total value.
Yes, sir.
I divide this value into 2 parts. One is AC component value, next one is a DC component value.
Okay.
What is this AC component value means? That is nothing but peak of the AC signal.
Yes, sir.
Okay. And then we left with DC component, on that we exercised it. And we assumed that number is Vm by mod Z.
Okay, sir.
And finally we concluded that this total number, AC component Vm by mod Z, DC component also Vm by mod Z, it came to be 2 times of Vm by mod Z.
Okay.
But in your circuit breakers, you take that as 1.8 times.
1.8 times.
In the circuit breaker design, rather than double, you take that as 1.8.
Okay, sir. And one more doubt, sir. I understood that why we are taking that relay at the end of protective zone, because that impedance will be high and current will be low, fault current. That same reason for taking circuit breaker nearby circuit breaker rating, is that the same reason for that?
No, actually, you have to design your breaker in such a way that it should not be damaged for any value of current interruption.
Yes, sir.
If you design that breaker based on the lowest fault current interruption, if it is interrupting higher currents, it will damage it, right?
Yes, sir.
Then based on what current you have to design the breaker?
For most severe fault.
That's it, most severe fault. At which location you will get the highest value of fault current again? Nearby the breaker.
Yes, the nearby breaker.
That's it. So while you are designing the breaker rating, you should take the fault nearby the breaker. Whichever the most severe fault you feel, that you have to consider. Maybe 3 phase.
Okay, sir. And high fault current value means more severe fault?
More severe fault.
Okay.
Right now, for our understanding, it's the most severe. As we move ahead, we come to know that severity term in an expanded way.
Okay,
with respect to stability, we will study. Those things are different.
Okay, and sir, last doubt. In this last topic, we saw that stator flux. So that stator flux is opposite to the sum of all that 3, phi SS plus phi FT plus.
Actually, that phi FT and phi DWT was produced now. These fluxes are opposing the stator flux.
Yes, sir.
And making the resultant flux as constant as time progresses.
Okay, sir.
Okay.
Yes, sir.
But you know, as time is progressing, phi FT, phi DWT are decreasing.
Yes, sir. Decaying.
Armature flux is penetrating more into the air gap, and resultant air gap flux is decreasing.
Okay. Okay, sir.
Okay.
Yes. Thank you, sir.
Yeah. Rajit. Rajit. Are you there, Prajit? Do you have any doubt, Prajit?
Yes, sir. Hello, sir.
Tell me, Prajit.
Yes, sir. 50 in slide number 51F, be calculated 2 time periods,
Okay.
and that's 7.35 and 17.35 milliseconds. Sir, which one do we consider?
That depends upon the way of asking the question. For example, in this question, in bracket they said give the answer between 0 to 20
Yes, sir.
milliseconds. And
Yes,
in
sir.
this question, they may give definitely some limit to ask. Is it 0 to 10 they want, or 10 to 20 they want? They will ask. According to that, you give the answer.
Okay.
Okay.
Yes, sir. Thank you.
Mubin. Mubin.
Sir,
Tell me, Mubin.
sir, you have explained this sustained short circuit currents and initial symmetrical RMS fault currents.
Yeah. Sustained current means steady state current.
Yeah, sir, can you please tell that how to understand that term?
How to understand the term is, I didn't get you.
It means you have explained from that waveform, na, sir.
See,
Sustained.
steady state means after reaching to steady state, you have to know how much is the current. That's it, right? For example, if it's a waveform, only AC component you are talking, right? You take only this blue color waveform.
Okay.
After reaching to steady state, what is the AC value? VMI moderate peak.
Yes.
At the initial condition, means nearby the instant of fault, what is the peak value? VMI moderate only, right?
Okay. Sustained means steady state only. Okay. No,
Steady state.
no, understand. Sir, then the second symmetrical RMS fault current, how you said, sir?
Only AC current.
Sorry, sir.
Symmetrical RMS current means only AC component.
Only AC component.
Only AC component.
Sir, you have
Where
mentioned
you are
initial-
asking? Where you are asking?
Sir, in the definitions only, sir. You have given.
That's what I am asking you. At what instant you want to find it?
At what instant? I didn't get you. Sir.
Symmetrical RMS current you have to get. Are you following the movie? What's my question is?
Sir, your voice just now breaks, sir. That's why I didn't understood.
What is the symmetrical RMS current? That's the question.
Symmetrical RMS current means.
That is nothing but AC component of fault current, RMS value.
AC
At what instant you have to calculate it? Initial.
Initial, sir. Sir, I don't know that we should calculate it initial.
We have written here. See that. Are you looking the board?
Yes, sir. I'm looking, sir, but unable.
We have written here initial, right?
Yes. Okay, sir. No, sir. Generally, we say symmetrical current, na, sir. Then why we are adding the tag initial? We calculate.
Because we need to have that RMS fault current only in the initial stage.
Later on also we have, na, sir.
Later on also we have. But see, during the short circuit, we are interested to find two things. One, how much is a steady state component? How much is a subtransient component? Okay. So during that subtransient time, we are interested to know the that's
okay, sir. Okay,
here
sir.
we have taken initial.
Okay, sir. Done, sir. Thank you, sir. One more, sir. This constant flux linkages theorem is what, sir? You use that frequently.
Simply, the resultant flux in the air gap will not change instantaneously. Resultant flux in the air gap will not change instantaneously. It will change only as time progresses.
It decays gradually as shown in that waveform. That, sir?
Yes. All of a sudden, it won't fall down to a low number. Or all of a sudden, it won't increase to a high number. Just like your inductor current.
Okay. Okay. Sir, this initial flux we have only rotor flux now, sir. That you have
Yes.
mentioned with steady state and field and damper winding.
That see
Three na,
to
sir.
make up this resultant as rotor flux only, this phi ft and phi dwt came into attack. This phi
No,
rotor,
sir. I mean, sir.
phi rotor is equals to phi ss plus phi ft plus phi dwt, such that these two fluxes are created, phi ft and phi dwt.
Sir, if we consider T 0 minus, then we don't have that phi ft and phi dwt.
We don't have
na,
only
sir.
phi rotor we have.
That you have mentioned that same point, na, sir. Then
Just
on the
after the
same
fault
point.
occurrence, just after the fault occurrence, resultant flux will be rotor
Sir,
flux
sir,
only.
Okay.
Resultant
Okay.
flux
Sir,
will be
then
rotor
it
flux
means
only.
before 0
But
that
listen, please,
phi
listen,
rotor
please.
should be less
Listen,
than
please.
that phi ss.
Kindly listen to me. Kindly listen to me. Before the fault occurrence, we have the rotor flux phi rotor. Just after the fault also,
Okay.
phi rotor only we have. Okay. So just
Okay.
that phi rotor we are rewriting as phi ss plus phi ft plus phi dwt.
My doubt is,
Tell me please.
okay, sir, my doubt is before the fault, we don't have any phi ft and phi dwt. Am I correct?
Yes.
Then it means that rotor, that horizontal line should lie below that point, na, sir.
Why?
Because we don't have phi ft and phi dwt.
What is phi ss?
Phi ss is this line only. That what
Very
very
low.
Yes.
That phi ss and phi ft, phi dwt gets added up, and that is phi rotor I am saying.
Yes, sir. That's true, sir. I'm not contempting it. What I'm telling is before that t is equal to 0, we don't have phi ft and phi dwt, na, sir. In the state, in that
Okay, you don't have it. You don't have it. Yes,
you
correct.
don't have it. Then what is the value of that flux? Only phi ss, na, sir.
Phi rotor I am saying.
Okay, that we call is phi rotor.
Phi ss is not equals to phi rotor, right?
Yes. Phi rotor is variable.
No, not phi rotor. Phi ss is different and phi rotor is different.
Okay.
This is phi ss line, right?
Yes, sir. That is phi ss line.
This is phi rotor line.
Sir, I am
See, you are
thinking that.
you are in an impression that for the phi rotor, phi ft, phi dwt got added up.
Yes, sir.
And armature flux was opposed.
Yes.
Then what is the resultant flux for you? Phi rotor plus phi ft plus phi dwt minus armature flux.
Okay, sir. Now it's a bit clear.
That armature flux phi ft, phi dwt gets cancelled out. You get phi rotor only in the air gap.
Yes, sir. Got it, sir.
Okay. Any other doubt in your movie?
No, sir. Thank you.
Bhavani.
Good evening, sir.
Good evening. Tell me, Bhavani.
Sir, in maximum momentary current equation,
Hmm.
IAC of T naught at T naught is equals to Vm by Z magnitude. There
Yes,
we
yes.
didn't take sign value, sir. We didn't include y.
Yeah,
sir.
from graph itself, you are getting that Bhavani.
For DC, we took sign.
Because I am unable to get what is this value in the DC.
Okay, sir.
From graph, I can't say DC value, but I can say AC value, right?
Got it, sir. Sir, sir, why? What is actually switching angle? Why we use this switching angle, sir?
If you don't consider the switching angle, means alpha equals 0 you take. What's the voltage signal you have? Vm sin omega t, right? Is your voltage signal.
Vm sin omega t.
Fault is occurring at which time?
We don't know.
0. If you keep the time t equals 0, what is this voltage value? Vm sin 0. 0.
Yes, sir.
Are you capable to do this fault analysis for a instantaneous voltage of Vm by 2? Now already you are saying fault is at time t equals 0. Are you following me, Bhavani?
Yes, sir.
Already you said that fault is occurring at time t equals 0. The time t equals 0, you are substituting here. You are saying that t equals to 0. Means you are doing fault analysis for only one condition, that the instantaneous source voltage equals to 0 at the instant of the fault.
Yes.
Yes or no?
Yes.
How to do fault analysis for an instantaneous voltage of Vm by 2?
You should have alpha.
For that purpose, you are keeping this alpha.
Okay, sir. Got it,
Else,
sir.
I said one more thing. Don't keep alpha. And don't say that fault is at time t equals 0. You say some t naught.
Then
Okay.
we don't need alpha.
I don't need alpha at the time. You keep t naught here. Vm sine omega t naught. You change the time t naught. Instant at which fault is occurring. Then obviously that instantaneous voltage will vary. Yes or no?
Sir, another doubt in initial conditions.
Hmm.
Just open that slide, sir, please.
Which slide? Initial conditions.
Conditions.
In this topic only.
Sir, when fault occurs at any time. The fault occurring in any time.
Any time.
Yes, sir.
Can you tell me the slide number?
No, sir.
This one?
After this, sir. After this initial
This one?
conditions. Yes, sir. This is.
Okay.
Sir, that at t is equals to 0, if that second line I didn't got it, sir, actually.
This one?
Fault at 0 plus or 0
0
minus
plus.
is equals to 0.
Because we
Just
have
to-
inductor in your circuit, right? Inductor you have in your circuit, and that inductor will not accept sudden changes in the current.
Yes.
So 0 plus time current and 0 minus time current will be equal.
That is for some time, no, sir? Short
For some
period.
time.
That is for
At that
short
instant.
period.
And that's what I am showing there. That at that instant,
Okay, sir.
at 0 plus time and 0 minus time, current is 0. But as time progresses, current will rise up and change.
I got it. Sir, what do you mean by sustained short circuit current?
Steady state. Steady state.
At Vm by Z, no, sir, then why you are
That's a
taking
Vm by
root
Z is peak value, right?
root 2, they are here.
Vm
we
by
are
Z,
taking-
Vm by Z is peak value, right?
Yes.
You need RMS, means you have to take peak by root.
Okay, sir. That's it, sir. Thank you.
Yeah, fine. Then we
Hello, sir.
tell me then we.
Sir, I have a general doubt, sir. What is actually the physical cause of the DC offset current, sir? Like I was analyzing, I came to I think that is it because that can't be any sudden change of current in inductor? That's why the DC offset current is being
That's the
produced.
reason. That's only the reason. Inductor will not accept sudden changes in the current flow.
Sir, but still, when fault is occurring, so there is a sudden change of current, sir. So how is this DC offset
At that
current?
instant itself, you don't have, right? Sudden change.
Okay, gradual change. Okay.
Resulted DC plus AC.
Okay.
Your
sir.
resultant fault current has been started from 0 only. Because you see, this is your DC component value at the instant of the fault, and this is AC component value at the instant of the fault.
Okay.
DC and AC. Summation is resulting to 0. In that way only you calculated the DC.
Okay, sir.
Okay. Any other doubt here?
No, sir.
Okay, fine. Tulsi,
Hello, sir.
tell me Tulsi.
Sir, 14F, sir.
Yes. Okay.
Sir, generally faults అంటేనే అన్బ్యాలెన్స్డ్ కదా సార్, మళ్ళీ ఇక్కడ ట్రిపుల్ ఎల్జీ బ్యాలెన్స్డ్ ఎలా అవుతున్నాయి ఒకసారి
Faults
చెప్పండి.
అంటే అన్బాలెన్స్డ్ అని ఎవరు చెప్పారమ్మా?
అంటే ఫాల్ట్ జరిగితే బ్యాలెన్స్ లో
ఎవరు
ఉండవు.
చెప్పారు అట్లాగా? There are unbalanced faults as well as balanced faults. రెండు ఉంటాయి.
మరి
ఓకేనా?
ఇవి ఓకే సార్, ఈ బ్యాలెన్స్డ్ ఎలా అవుతున్నారో ఒకసారి ఎక్స్ప్లెయిన్ చేస్తారా సార్? ట్రిపుల్ ఎల్జీ
What do you mean by triple L fault?
Three phases get short circuited.
Three phases get short circuited. What is impedance, load impedance of phase A?
Z.
0. Shorted, no?
Yes, sir. 0.
Load impedance of phase B?
0.
Load impedance of phase C?
0.
All the three are equal?
Yes, sir.
Your system is balanced?
Yes, sir.
Balanced fault.
సేమ్ ఇంకా ఇక్కడ ట్రిపుల్ ఎల్ జీలో కూడా 0 అవుతుంది కదండి సార్ అంత.
Same. Yes.
ఓకే గాట్ ఇట్ సార్. ఇన్ 27F సార్. సార్ ఇక్కడ ఇది ఒకసారి ఎక్స్ప్లెయిన్ చేస్తారా సార్? T = 0 దగ్గర అవుతుంది అన్నారు కదండి.
What's the doubt in that?
సార్ మామూలుగా ఫాల్ట్ అని ఒక 1 minute సార్. I'm not getting sir what I got doubt in that. Okay. After again. Sir 35F sir. Sir before. Sir here sin omega t minus theta minus alpha we are writing now sir. That alpha you explained before sometimes sir.
Okay.
I'm not getting that. Can you explain once?
Just now I explained about alpha, right?
Yes sir. In that time only I also got doubt sir.
Now see, if you don't consider that alpha, or else you say alpha equals 0, then you will be saying your instantaneous voltage will be 0 only.
Yes sir.
Yes, you can't do fault analysis for this instantaneous voltage, for this instantaneous, right?
Yes sir.
So that if you add alpha to this omega t, so you get sin of omega t plus alpha, then you get that voltage as Vm sin alpha.
Yes sir.
By varying that alpha, it is possible to take up different instantaneous voltages at which the fault is occurring.
Actually, when fault occurs, V becomes 0 now, sir.
Why V becomes 0?
Yesterday we...
Where it will become 0?
Short circuit fault occurs, then V becomes 0.
Where? At which location?
At load side, sir.
At fault location?
Yes, sir.
Not at source, right?
No, sir.
This is source.
Okay.
Okay.
Got it, sir. Sir, in 47F, sir. Sir, can you explain that? ఇక్కడ నుంచి చెప్తున్నాం కదండి సార్, డాంపర్ రెసిస్టెన్స్ డిక్రీజ్ అవుతుంది అని చెప్పి మనం ఫైనల్ లో.
Not in this slide, right?
Not in this slide, sir, but formula
Damper resistance.
Damper resistance 61F, sir.
Okay.
No, sir. Yes, sir. ఇది ఒక్కసారి.
So generally, if time constant is low, then it will decrease fastly, right?
Time constant low. Yes, sir.
So damper bars will have no time constant.
Okay, sir.
These are simply bars, like conductor bars. You don't have a coil.
Yes, sir.
So inductance of those damper bars is very low.
Okay.
So time constant is very less.
Less.
So that the damper winding transient flux will reach to 0 very quickly as compared to field winding transient flux.
Okay, sir.
Okay.
Got it.
Any other doubt you have?
సార్ ఇంకొక డౌట్ ఏంటంటే, మీరు ఒక సెంటెన్స్ ఎక్స్ప్లెయిన్ చేశారు కదండి సార్, ఫ్రమ్ ఇన్స్టెంట్ ఆఫ్ షార్ట్ సర్క్యూట్ ఆర్మేచర్ ఫ్లక్స్ క్రియేటెడ్,
resultant flux will decrease.
దాని కింద ఇంకో సెంటెన్స్, నో ఇన్స్టంటేనియస్ చేంజ్ ఇన్ ద ఎయిర్ గ్యాప్ ఫ్లక్స్ అని.
No instantaneous change. Yes.
సార్ ఇప్పుడు ఒక ఫాల్ట్ జరిగినప్పుడు మన దగ్గర రోటర్ ఫ్లక్స్ రొటేట్ అవుతా ఉంది కదండి సార్, సేమ్ డైరెక్షన్ లోనే ఫ్లక్స్ రొటేట్ అయినప్పుడు మనం రోటర్ దగ్గర నుంచి చూసినప్పుడు రెండు సేమ్ డైరెక్షన్ లో ఉన్నాయి కాబట్టి రిలేటివ్ మోషన్
0. Okay.
అప్పుడు మనకి ఫాల్ట్ జరిగినట్టు కూడా తెలియదు కదండి సార్ అసలు.
What you are saying? Please repeat again.
సార్ మనం ఏం చెప్పంటే రోటర్ దగ్గర
How you know fault is occurring or not? Fault has occurred or not? How you know? Are you capable to measure flux or current?
కరెంట్.
Correct. So if you are seeing current beyond your limits, you can say there's a fault.
ఓకే. కానీ ఇక్కడ ఫ్లక్స్ కాన్సెప్ట్ నుంచి మనం కరెంట్కి వెళ్తున్నాం కదండి సార్.
No. Why we are discussing about this flux concept is
Ah.
to tell you about armature reactance is variable with respect to time.
ఓకే.
Armature reactance is variable with respect to time. It's not a constant number like a inductor or like a transmission line inductance.
ఓకే.
It is time varying number. To tell about that only, we are discussing about armature reaction here.
ఓకే సార్.
Okay.
అయితే ఫ్లక్స్ తో మనకి రిలేషన్ లేదా సార్ ఇక్కడ అయితే?
No, flux we are not going to consider an identification of fault.
ఓకే సార్.
Okay.
ఓకే సార్.
Any other doubt you have?
నో సార్, థ్యాంక్ యూ సార్.
Pallavi.
Sir, actually, I have one doubt in one question. Means that symmetrical components they give that ask about one matrix. Means
That matrix you said.
I send you on WhatsApp.
What's the doubt you have in that?
Yes, sir. I stuck on one step. That's there are 3 matrices are there, 3 by 3, 3 matrices. So how can I solve, sir? I solve at my conventional method, so it takes more time, sir. So if there is any shortcut to solve that matrix, sir?
One shortcut, what I can say is, which matrix is given to you? Is it symmetrical component matrix or ABC matrix in the question?
They give ABC, sir.
I think symmetrical.
Also, they symmetrical. They give ABC as well as symmetrical, sir. 2 or 3 matrices and they give relation.
In the question, they have given P and 0.
Yes, sir.
In the question, suppose we define the sequence transformation between ABC and P and 0 variables as follows.
Yes, sir.
FA, FB, FC equals to K into 111 alpha square alpha 1 alpha square 1 FP, Fn, F0.
Yes, sir.
Are you looking that?
Yes, sir. Yes, sir.
Then what is VP, Vn, V0? Read the problem. VP, Vn, V0.
0.500, 0.50,
Okay.
0.0, IP, IN, I0.
Okay.
And they also give ABC.
And he said that VA, VB, VC equals to Z into IA, IB, IC. He's asked
yes.
Z matrix.
Oh, yes, sir.
How that symmetrical component matrix looks to you? VP, Vn, V0, 0.500, 00, 0.50, 002. These are looking like sequence impedances, right?
So, sir, that itself answer.
No, just listen.
Okay.
The 0.500, 0.50, 002.
Yes, sir.
That looks to be symmetrical components impedance matrix.
Yes.
Because that is giving relationship between the positive, negative, zero sequences to ABC.
ABC, yeah.
So he said FP, Fn, F0 is equals to 0.500, 0.50, 002
Yes.
multiplied with V. Yes, V. IP, IN, I0.
Yes.
Okay.
Yes.
So what is this impedance we have to call? Positive sequence impedance?
Positive. Yes, sir.
What is this impedance?
Negative.
Negative.
Means
What
negative
is this impedance?
sequence. Zero sequence.
0. What is general formula for ZP? If you have ABC impedance and all,
1 by
ABC 3,
1 by 3.
ZS minus ZL.
ZS, ZS.
Zn is also ZS minus ZL.
Yes, sir.
Z0 is
Z-
ZS plus 2Z.
Yes, ZS plus 2.
So the first number is 0.5.
Mhm.
Next number is 2. Okay.
Yes,
So
sir.
how is your ZABC matrix? ZS, ZM, ZM,
ZS.
ZM, ZS, ZM. So just you calculate the ZS and ZM values here. Calculate ZS and ZM values, fill into the matrix.
Okay, sir. Okay, sir. Thank you.
Understood what I said?
Yes, sir. Because that method is really very lengthy, sir, if I calculate in conventional method.
Whatever the method you solve, that is a perfect method even compared to this.
But sir, this is very lengthy, sir. It takes more time.
But still. Because why it is so means they have given some constant K there.
Yes, sir.
Don't know about the constant K exactly. If original answer is in terms of K, then definitely there's a chance of going wrong, right? I think fortunately no option is with K.
No, sir, they ask.
What is the fourth option given there?
Fourth option, K square by 3.
K square by 3 numbers.
In bracket 1.0 minus 0.5 minus
yeah.
0.5.
And no option will match.
Yes, sir.
If you do by this method, you will get this number 1, 0.5, 0.5, 0.5, 1, 0.5, 0.5, 0.5, 1.
Yes, sir.
So this type of matrix only one exists in the whole.
Yes, sir.
That is without K.
Yes, sir. Two are there in options.
That's what I'm saying. B, na?
Yes, sir.
Is there any option of this matrix?
Yes, sir. Second.
What is that? Second. That's what I'm saying. B, right?
1.0. Yes, sir.
B is the answer.
Okay, sir. Thank you.
Mm-hmm.
Yes,
Are you listening to me?
yes, sir. Yes, sir. Thank you.
Yeah.
Yeah.
Sai Charan. Sai Charan Reddy.
Hello, sir.
Tell me.
Hello, sir. Good evening, sir.
Good evening.
Sir, in CB rating versus fault level, sir.
Okay.
Circuit breaker rating versus fault level.
Tell me what's the doubt here?
Sir, I did not understand the perfect difference between them, sir.
Circuit breaker rating we have to calculate based on the current flowing in the breaker.
Sir, I have one more doubt in this only. CB is protecting which systems are actually?
Both.
Circuit breaker.
Both systems.
So you used a word like interruption current, na, sir?
Interrupting current.
Interrupting current. Interrupting current means
how much
when
current is breaking?
Circuit breaker current is equal to the
breaking current.
So interrupting current means it won't.
Tell me.
Sir, I did not understand why. Sir, if the fault occurs in right side, you told that fault occurs right side of circuit breaker. You told that IF and IF1 flows through the circuit breaker, na, sir? I did not understand why.
Why?
Why IF1, sir? IF1 plus why not IF1 plus IF2?
Why not?
Why not sum of both of them?
Where you are keeping breaker, is it on line or on fault?
Sir, on line, sir.
Practically, where you keep the breaker, is it on line or on the fault element?
On line, sir. After placing the brake only, we will get
on line. So whatever
yes,
the current flow in the line, that has to be interrupted by the breaker, not the fault breaker.
Okay, sir. So this fault current two bypasses before reaching the circuit breaker,
Before
sir.
Before reaching the breaker, it's going to fault.
Yeah, sir. I have doubt at this point only, sir. So
listen, Sai Charan. Just go with the fault current IF1. It is going like this, going in the breaker, going into fault. Okay? Go with the IF2 like
yes,
this, coming like this, fault, grounded. But that IF2 is not going into CV. That's it. KCL application.
Okay, sir.
Tell me
in this
any
case,
doubt.
In this case, if the IF2 bypasses through the ground, then we say that system 2 is not protected, sir. It is with ground fault, LG fault.
System 2 is not protected.
You told that both.
Take care of that fault current. System 2 will have their own breakers and relays.
So we can indirectly say that if the fault current fault is right side of circuit breaker, it is out of its reach, sir.
Of its reach.
Reach means it is not in protected area of circuit breaker zone, protected zone. I am confusing in this one only, sir. Like, this is my doubt, sir.
See, breaker is getting open does not mean that the fault is getting cleared, right? If the breaker is getting opened in a system, is it the mean to say fault is getting cleared by the breaker? May or may not be. That how can I say? Ultimately, fault current should drop down to 0. Then only I can say that fault was cleared by the breakers.
Yes, sir.
So the conclusion what you have to make here is this circuit breaker alone, what you have chosen here, will not provide a protection for both the systems from the fault what you have considered.
Okay, sir.
Okay?
Yes, sir.
Understood my statement, Sai Charan?
Yes, sir. Yes, sir.
That is the
We
conclusion
just
you
took
have to make.
as an example to. Yes, sir. Yes, sir. Sir, can you please conclude how directly the difference between circuit breaker rating and fault level?
That's what I am saying you. Circuit breaker rating on what current you calculate?
Circuit breaker rating, the current.
On basis of what current you calculate it?
Fault current.
When you are saying fault current, then what you have understood from this? Sai Charan? Sai Charan?
Sir, hello, sir.
Just listen to me. On basis of what current you calculate the circuit breaker rating? Is it fault current or current flowing in the lines during fault? Sai Charan, are you there?
Current flowing through circuit breaker, sir.
Current flowing through circuit breaker. Where you are keeping breaker? On the lines.
On the line.
Means you have to calculate current flowing in the lines, which will pass through breaker also, based on which you have to calculate the breaker rating.
Yes, sir. Yes, sir. So in fault
level is decided based on the fault current.
Yes, sir.
That fault current may be equals to line current or maybe more than the line current in this type of situation. For example,
yes.
You take one system like this, only one line, there is no other system, and is a breaker. Okay? And for example,
yes,
if you take fault at this place, this is a fault current IF.
Both will be equal. Both will be equal.
Both will be equal at that time. That's it. Simple.
Yes, sir. And another one is the difference between the both of these. We took a pre-fault for fault level, and we took phase voltage for
breaker rating.
phase voltage
Breaker
for
rating.
circuit breaker
Breaker
rating.
rating. Designing. At the design stage, we have to consider rated things, right?
Yes, sir. Yes, sir.
Yeah.
So pre-fault condition means this will also be the phase voltage only,
Phase
sir.
voltage,
Phase or line.
default voltage per phase.
So why did you especially mention that it is
It may
pre-fault
be more
voltage?
than rated voltage or maybe less than rated voltage. That depends upon the operating condition.
Operating, yes, sir. Yes, sir. Yes, sir.
But the first one is designing one. Second
Yes,
one
sir,
is
yes, sir.
operating.
Yes, sir. Yes, sir. Like base value and operating value.
Okay, you can assume that way for
Yes,
your
sir.
understanding, but don't write it anywhere.
Yes, sir. Yes, sir. Sir, you told something when pre-fault is not given in the problem. Pre-fault voltage.
If the pre-fault voltage is not given, we assume that as 1 per unit. It's a common assumption.
Sir, what? Come again, sir, please.
Sai Charan. If there
Yes,
are
sir.
no resistances given in the data, only reactants are given for apparatus.
Yes, sir.
Will you neglect resistance or not?
Yes, sir. Neglect.
They have not given operating voltage of the system. And they are asking us
Yes,
to
sir.
calculate what is the fault current.
Okay, sir. So we assume rated current only. Rated voltage only.
Rated voltage.
Yes.
1 per unit.
Yes, sir. Yes. Yes, sir. I got
There
clarity,
is no
sir.
chance. If there is no chance, we have to take something. That's it.
Yes, sir. Yes, sir. Sir, in page number 34F, sir.
Tell me.
IDC, how it is. Okay, sir. Clarified, sir. Sir, in page number 36, sir. Sir, here steady state component means can we say that steady state component means DC will be 0 at steady state. After
DC comes 0, whichever the normal sinusoidal signal we have, that itself is steady state.
Okay, sir. Okay, sir. Sir, in page number 55F, sir. 55. Sir, yeah, I think this is the 60F, sir.
No, where you want? Where you have the alternator?
No, sir. You wrote a generalized equation. You wrote a generalized equation of fault current at T is at 0 plus time.
Is this you are looking for?
No, sir. You wrote with a red marker with at T is equals to 0 plus.
Is this?
Sir, I'll ask my doubt. I'm not getting
is
that,
this
sir.
one?
No, sir. Yes, sir. This one only, sir. For fault at T, sir. You told that for fault at T is equals to 0 plus. According to the inductor, you told that IDC will be 0. IDC or something. We took that in we took that for obtaining K through initial conditions. In that condition, we took that for finding K values in initial conditions, we took T is equals to 0 plus only, na, sir. That. Hello, sir.
Yes.
So here. Sir, can you please open that initial condition?
I'm unable to listen to you, Sai Charan.
Hello, sir.
I'm unable
Hello.
to listen.
Hello.
Tell me, Sahajari, tell me. Tell me
Sir,
now.
can you please open that initial condition, sir? Hello, sir.
Okay. Tell me what's the doubt you have here?
Here, I faulted. So this is same as the that we do in control systems for obtaining the transient conditions in RL and RC circuit. This one only, sir.
General, regular initial
all the
conditions
process.
application.
So
Regular
I was
initial
confused in
conditions.
that if yes, sir. But I was confused that if IF is 0 at t is equals to 0 plus, then how did that equation we got? Like that, I was confused.
Okay.
Yes, sir. Okay, sir.
Okay.
Sir, if you define alpha in a generalized manner, we will only take alpha for finding where the for which instant of input the fault is occurring, na, sir?
Find out fault current for different instantaneous voltages.
So what is that use, sir? If you find input, then input. If you find in which input the fault is occurring, then what is the use of that, sir?
Worst fault occurrence. You have to find the worst fault occurrence and the best fault occurrence, right? We have to find out what is the worst value of fault current, worst fault occurrence.
Okay. For worst fault occurrence, we can take directly maximum voltage of that, no, sir?
How come you know? We can't say that, right?
So for finding the maximum value of that also. So for that one also we want alpha.
Alpha.
Okay, sir. Sir, I'm asking that for that one also we want alpha indirectly.
Yes.
Okay, sir. So for designing, this alpha works for designing only, sir.
Designing, yes.
Yes, sir. Thank you, sir.
Okay. Any other doubt here?
No, sir. No.
Yeah.
Hello, sir. Sir. Hello, sir.
Vaishnavi.
హలో సార్ సార్ ఈ పేజ్ లోనే సార్ ఇక్కడ t ఈక్వల్ టు 0 ప్లస్ దగ్గర ఇది ఎలా రాశారు సార్? IF ఆఫ్ 0 ప్లస్ ఈక్వల్ టు 0 ఎట్లా అవుతుంది సార్? అది అర్థం అవ్వట్లేదు సార్.
Why can't it be?
అంటే ఫాల్ట్ అక్కర్ అయిన తర్వాత కరెంట్ ఉంటుంది కదా సార్, కరెంట్ మనకి వోల్టేజ్ అనేది
At which instant you are writing it?
Just
at which instant you are writing?
Just after the fault occurs.
At which instant? Just at the instant of fault occurrence. Because of inductor does not allow sudden changes in the current. Current will remain 0, right? At time t equals 0 minus and 0 plus. Correct.
అదే సార్ అప్పటి నుంచి ఆ పాయింట్ చెప్తున్నా నాకు అర్థం అవ్వలేదు సార్. అందుకని అంటే ఇప్పుడు ఇండక్టర్ అనేది సడన్ చేంజ్ అని అలో చేయదు కాబట్టి కరెంట్ అనేది
sudden changes in current it won't yes remains 0 at that instant.
Fault current
from that instant it will start rising.
సార్ మరి 45F సార్ 45F సార్ మరి ఇక్కడ అప్పుడు ఈ IF అనేది అట్ ఎనీ టైం కదా సార్ ఫాల్ట్ కరెంట్ అనేది ఇక్కడ అప్పుడు అంటే హెడ్డింగ్ అప్పుడు హెడ్డింగ్ t ఈక్వల్ టు 0 ప్లస్ అని ఉండకూడదు కదా సార్? అప్పుడు ఇన్స్టంట్ అని మనం అనుకుంటాం.
These conditions I am writing for the fault at time t equals 0. If you want to keep t equals 0 plus here you will get 0. There is that.
సార్ మరి లాస్ట్
time t equals 0 you will get 0.
సార్ మరి లాస్ట్ ఎక్స్ప్లెయిన్ చేశారు కదా సార్, అది రోటర్ స్టేటర్ వేసి ఆ స్లైడ్ ఒకసారి తీయండి సార్. అక్కడ మనకి ఎప్పుడైతే ఫాల్ట్ ఫిగర్ కి సర్వీస్ సార్ ఎప్పుడైతే ఇక్కడ ఫాల్ట్ అక్కర్ అవుతుందో అప్పుడు స్టేటర్ ఆర్ఎంఎఫ్ అనేది రోటర్ మీద ఎఫెక్ట్ అయ్యి రోటర్ లో ఈఎంఎఫ్ అనేది ఇండ్యూస్ అయ్యి అది డాంపర్ వైండింగ్స్ మీద ఫీల్డ్ వైండింగ్స్ మీద ఎఫెక్ట్ చేసి దాని వల్ల కరెంట్స్ ప్రొడ్యూస్ అయ్యి అది ఆపోజిట్ అది ఆర్మేచర్ వైండింగ్ కి అపోజింగ్ గా ఉంటుంది. అందుకని మన యొక్క రిజల్టెంట్ ఫ్లక్స్ అనేది డిక్రీజ్, అందుకని మనకి రిజల్టెంట్ ఫ్లక్స్ అనేది అదే సార్. అంటే ఇట్లనా కాదని. ఓకే సార్.
ఓకే. ఓకే.
హలో సార్.
దీక్ష.
Yes, sir. Sir, on 50 slide, 50. Already answer for this, I not understand. Why we take minus 180?
Minus
180 for cos.
Two options I said. Two options.
First is 180.
Cos 180 is minus 1. Cos of minus 180 also minus 1 only, right?
Okay.
There are many options here. Many options, but you have to take one of the suitable one.
Cos inverse minus 1 is 180. Then why we take minus 180?
I'm saying you, if it's a sinusoidal signal, you will get many answers, right?
Okay, sir.
For example, I will write the third one also with the 360 plus 180 degree. Getting Diksha, what I'm saying?
Many options.
Many options you get, but you have to give the answer according to its requirement. As you said already, 0 to 20 milliseconds, your answer will be 12.35. That's it.
And sir, second step, I'm not understand. 222.3 into pi divided by 180.
What do you have doubt in that?
This step, I'm not understand.
Why? That angle is in degree. Angle is in degree. Omega t is in radians.
Yes.
So you have to convert that angle to radian, right?
Yes.
That's why you multiplying that with pi by 180. Okay, Diksha?
Yes, sir. Thank you.
Gurudatta.
Yes, sir. Good evening, sir.
Good evening. Tell me.
Sir, in maximum momentary current, we got from graph in instantaneous SC current equal to Vm by root Z, Vm by mod Z. But for DC instantaneous maximum, we consider as alpha equal to 0.
Consider it.
That means, sir, only in alpha equal to 0, we got maximum DC instantaneous.
Yes.
For other switching angle, we can't get the maximum.
You don't get it. No.
Okay, sir. Okay, sir. Got it.
Other switching also will get.
But we only consider here.
Other than alpha equals 0, other switching also will get with a condition of this, right? This one. Alpha equals to theta minus pi by 2 if you have, then we will get it again.
Alpha.
Are you there?
Okay. Yes, sir.
With this condition you will get, right? Alpha equals theta minus pi by 2.
If we put alpha equals,
it is even better condition. It is even better condition as compared to alpha equals 0.
Okay, sir. There theta cancel, only remain pi by 2.
Pi by 2 we have, sin pi by 2 is 1.
Then sir, sin pi by 2 1. Direct we got 1.
Yes.
Yes, sir. Got it, sir.
Okay.
Okay, sir.
Okay, fine. Anil Kumar.
Sir.
Tell me, Anil Kumar.
Sir, in substantial, it is occur only for first two.
Didn't get it. Please repeat again.
Transient. Sir, in substantial state, sir. So in substantial state,
transient state,
it is only available for first 2 cycles, sir. And the DC component is highly decayed as compared to the transient state. That point I did not get.
No, wherever the rate of decay in the DC component is very, very high, that initial period we are named separately as subtransient.
Okay, sir. Okay.
Remaining period also we have a DC decay component that we are naming as transient per se.
Okay, sir. Sir, the relay and the circuit breaker, we are designed that based upon our transmission line rating only, sir.
No, fault analysis.
Fault analysis.
That's what we are discussing now, right?
Okay, sir.
Okay.
Thank you, sir.
Any other doubt you have, Malhotra?
Oh, no, sir.
Okay.
Thank you, sir.
Harshavardhan.
Sir.
Harshavardhan.
Sir?
Tell me, what's your doubt, Harshavardhan?
Sir, ఇది momentary current ఉంది కదా సార్. సార్ momentary current అంటే ఇప్పుడు అంటే స్విచ్ క్లోజ్ చేసినప్పుడు హైయెస్ట్ మాక్సిమం కరెంట్ అంటే అదే కదా సార్, మాక్సిమం RMS కరెంట్ సార్. సార్ అయితే ఇప్పుడు సర్క్యూట్ బ్రేకర్ లో ఇప్పుడు మేకింగ్ కరెంట్ ఉంటది కదా సార్.
That's a maximum momentary current. Maximum momentary current.
అంటే రెండు ఒకటేనా సార్ అవి?
Maximum momentary current and making currents are similar.
ఓకే ఓకే. అంటే సార్ ఇప్పుడు మాక్సిమం అంటే ఇప్పుడు మీరు మొమెంటరీ కరెంట్ ఈక్వల్ టు √2 ఇంటూ 2 ఇంటూ అది బ్రేకింగ్ అది సిమెట్రికల్ కరెంట్ అని ఇచ్చారు కదా సార్. అంటే ఇప్పుడు అది మాక్సిమం అంటే మాక్సిమం మొమెంటరీ కరెంట్ సార్.
Maximum momentary current.
సార్ అయితే ఇది మాక్సిమం మొమెంటరీ కరెంట్ అంటే ఇప్పుడు మేకింగ్ కరెంట్ ఈక్వల్ టు 1.8 ఇంటూ √2 కదా సార్. అది అంటే
డిజైనింగ్ సర్క్యూట్ బ్రేకర్ డిజైనింగ్ కి 1.8 తీసుకుంటారు.
ఓకే. అంటే ఇప్పుడు మామూలుగా ఇప్పుడు ఏదైనా ప్రాబ్లమ్ లో ఇప్పుడు మేకింగ్ కరెంట్ అడిగారు
if you are getting a problem on circuit breaker, for example if you have a 2000 MVA 33 kV 3 seconds circuit breaker, what is the making current is asking?
Yes sir.
Okay, then you take 1.8 into 2 in 1.8 into √2 into symmetrical breaking current.
Okay.
Okay, if he is giving a problem with resistance, inductance and so on, like transmission line.
Okay.
And he's asking what is a maximum momentary current, you take double.
Okay. Means we should take 2 into
according
√2.
to the data how they will give. If they have given directly for circuit breaker, you take 1.8.
Okay sir.
If they have given some transmission line or something like this and he is asking what is the maximum momentary current, you take two times.
Okay sir. Okay sir. Thank you. Okay.
Yeah.
Thank you sir.
Okay. Bharati.
Hello sir.
Tell me Bharati.
Hello.
Tell me Bharati.
Sir, in alternate we have this fixed fault no.
Can you repeat again? Can you please repeat again? I am unable to listen to Bharati. Bharati. Are you there? Anybody have doubts? Please raise your hands quickly. Bhavani.
Hello sir.
Tell me Bhavani.
Sir, initial condition slide లో మీరు IF లాస్ట్ BM by Z sin DC plus AC అనే అది ఒక ఈక్వేషన్ వచ్చింది కదా సార్. T is equals to 0 కండిషన్ సబ్స్టిట్యూట్ చేశారు. సార్ ఇప్పుడు వచ్చిన రిజల్టెంట్ IF అది ఇనిషియల్ కండిషన్స్ కండిషనా లేకపోతే T is equals to 0 దగ్గర వచ్చే IF లేకపోతే ఎక్కడ?
For the fault current more than time t equals 0. At any time you can calculate from that side. Just to calculate the value of K, we have taken the initial condition.
Okay. Sir,
Once after getting it, it's your resultant fault current only, which will give fault current at any time.
ఓకే సార్, ఇంకోటి మీరు ఇందాక ఆల్టర్నేటర్ లో ఇప్పుడు షార్ట్ సర్క్యూట్ ఫాల్ట్ వస్తే అక్కడ రొటేటింగ్ మ్యాగ్నెటిక్ ఫీల్డ్ ఫ్లో అవుతుంది అన్నారు కదా సార్. సార్ రొటేటింగ్ మ్యాగ్నెటిక్ ఫీల్డ్ అది ఆల్టర్నేటింగ్ ఇన్ నేచర్ ఉంటుంది సార్.
Rotating magnetic field is not in alternating. If you are sitting on the rotor, it will look like a static, right?
అంటే ఇప్పుడు అది స్టార్టర్ నుంచి వచ్చే ఫీల్డ్ అయితే ఆల్టర్నేటింగ్ నేచర్ ఉంటుంది సార్.
At a particular point, it will experience the same value of flux, right? On the rotor.
At a particular point, మొత్తం కాదు కదా సార్.
We are sitting on the rotor, it is rotating. The stator flux is rotating continuously in the air gap.
Okay.
If you are sitting on the rotor, how that flux looks to be for you?
Same.
Static.
Static.
Even though it is sinusoid.
అది ఫ్లక్స్ హాఫ్ సైకిల్ వచ్చినాక మళ్ళీ రివర్స్ తిరుగుతుంది కదా సార్, అప్పుడు సేమ్ ఉండదు కదా సార్ రొటేటింగ్. అంటే మనం ముందుకు వెళ్తుంటే అది వెనకాలకి వెళ్ళిపోతుంటుంది.
Both are rotating in same direction, right? Both are rotating in same direction.
Once just show on the slides.
Both are rotating in same direction. Stator flux and rotor.
Okay.
Both are rotating in same direction. Obviously, at any point, if you are standing at some point on the rotor, at a particular point, it will experience same value of stator flux, right?
Okay. I got it.
Just if you want, you draw one sinusoidal waveform in the air gap.
Okay, sir.
Okay, and you take a rotor.
Okay.
Then you feel that both are rotating with the same speed.
Okay.
For example, you stand at North Pole, check how much is armature flux. That will be remains constant for all the time.
Okay, sir. I understand. Okay.
Okay.
Thank you, sir.
Yeah. Any other doubts? Please raise your hands. Any other doubts? Anil.
Sir, in circuit breaker rating, we can design the total current flowing through the line. Like this, we can design. That way only we can design the circuit breaker rating. Sir.
Yes.
Sir, relay we are connecting a far away from the source, sir.
Relay while you are connecting.
Yes, sir.
I didn't get your question, Anil. Once again, please repeat.
Sir, we can connecting the end of a productive zone, sir. That point, sir. Far end of a productive zone.
After where you want to keep the relay, that's your wish, first of all. After keeping relay at some particular place, how much length of transmission line you have to protect by the relay, again your selection.
For that purpose, we have to calculate the transmission line.
With respect to that protective zone, then you have to calculate your fault current, relay setting, pickup current, and so on.
Okay, sir.
Okay.
Yes, sir. Thank you, sir.
Sir.
Tell me, Mubin. Tell me, Mubin.
Sir, am I audible?
Tell me.
Sir, in transmission line sequence networks, we have IA into Z, delta VA equal to IA into ZS plus IB into ZM and IC into ZM. Sir, the IB into ZM, how we got? Please tell us.
Yesterday also you asked the same note, right?
No, sir. Yesterday I didn't ask any doubt.
Okay. See, if if two conductors are one beside the other, because of mutual linkages from one conductor to other conductor, there is an induced EMF.
Yes.
Are you listening to me, Mubin?
Yes, sir.
Are you listening to me?
Yes, sir. Am I audible?
So what is it mutual induced EMF formula?
N d phi by dt. Sir.
What is the mutual induced EMF formula?
M d phi by
dt. MDI by dt?
Yes, sir. MDI by dt.
MDI by dt.
Okay.
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 So what is that current you should take? Is it its own conductor current or other conductor current?
Okay, other conductor current.
That's it. IB into JW.
Yes, sir. Got it, sir. Sir, one more, sir. Sir, if we connect a CT in any of the phase and measure the current flowing through it, then it gives that only IA or along with that induced EMFs, all it will give, na, sir? Sir?
If you keep one CT to measure the current.
Yes, sir. In any one phase, then it reads.
Okay.
It reads current in that phase. Option A. Option B. Current in that phase when it is isolatedly operated, it will flow some 100 amperes like that. Now it is operated with 3 phases, sir.
Please send that question to my. You please send that question to my WhatsApp once.
Sir, no, there's no such question. I just now got that doubt while analyzing these things, sir.
Is it a question or you are asking?
I'm
it's
asking
your own thing to ask.
I'm asking my doubt based on this mutual impedance. Based on mutual impedance only, sir. I'm asking on my own. Sir.
Tell me.
Sir, we have a line and we have operated on isolatedly. It's carrying 1000 amperes, sir. And that same line is connected along in 3 phase, sir, now. And that phase current is either 100 amperes or more than 100 amperes. It means based on the concept that
listen to your question completely. There is some network issue. Do we have that copy?
No, sir.
You tell me, you are saying 100 amperes, 1000 amperes something. Please tell me once again.
Okay, sir. Yes. Sir, we have a single line, sir, and it's carrying 100 amperes of current.
Okay.
100 amp. Now we are operating. Now we are operating on same voltage, same current, same power in 3 phase, the same line.
Same line.
Same line in 3 phase. Now, how much current it carries? Either 100 amperes or due to this mutual impedance and all, it will carry more than that.
100 amperes only. 100 amperes only.
Sir, we have discussed about this due to mutual inductance, current will induce and it will flow.
That is voltage drop. Voltage drop, not current induce. Voltage will induce, right?
Voltage will increase, sir.
Voltage will induce. Voltage will induce, that will act as a voltage drop.
Sir, okay, sir. Now understand.
Voltage will induce, that will act as a voltage drop because of mutual effect.
Sir, voltage will induce, and if there is a closed path, current will also flow, na, sir. Sir,
it will act as a drop only, right? Who is going to decide this current? Your load.
Yes, sir. I'm telling that all the parameters are constant only, sir. I want to know whether due to that impedance, it is affecting that current value or not. Just that's my question.
See, simple. Because of the mutual linkage, we have a voltage drop in the conductor. That's it. What's the doubt you have in that further?
Okay, sir. I will. Okay, sir. Sir, one more, sir. Today we have solved a problem. Yes, sir.
Because of mutual linkage. Listen to me once, Mubin.
I am listening, sir.
There's a network issue with you.
Sir, you are audible to me. Sir, you are audible.
Yeah. See, whenever you have some mutual linkages, there is some induced EMF in the conductor.
Yes.
That will act as a voltage drop.
Yes.
Yes. Then what's your doubt here with respect to current? That current is decided by load.
Okay.
Then you said already 100 amperes current fixed.
Yes. Then
definitely this current will not change, right?
Okay. I am thinking that due to that induced EMF, some extra current will flow. I am thinking in that way.
That will act as a voltage drop, but increment you don't have.
Okay, sir. Sir, today we have solved a problem. VA equal to VM cos omega t plus 30. He had given to take that as reference voltage. If he doesn't give that to take as reference voltage, we take VM sin omega t plus alpha, na sir, or only VM sin omega t.
Then it's a nonsense question completely. They should give a reference voltage to us, right?
They must give us, sir.
Without
Otherwise,
giving
we
reference
can't.
voltage, you can't find. They must give reference voltage. Without giving that, you can't take your arbitrary assumption. If you
Yes,
take
sir.
sine, you get one answer. Cos, you get some other answer.
Okay, it means in
Then
question.
it's a lack of clarity.
Okay, sir. That
They
now,
should give. They should give.
okay, now cleared, sir. Thank you, sir.
Yeah, yeah. Sridevi. Sridevi, are you there? Do you have any doubts, Sridevi?
Sir, good evening, sir.
I am unable to listen to you, Sridevi. Sridevi? Sridevi, I am unable to listen to you. Do you have any doubt?
Hello.
Sridevi, are you there? Do you have any doubts, Sridevi?
Yes, sir. Hello, sir. Hello.
Tell me, Sridevi.
Sir, I have a
Tell me,
doubt
please go ahead.
I have a doubt in symmetrical components, sir. Sir, the question is, if in an unbalanced three-phase supply, star connected load, the line-to-line voltages have been given, sir. VAB, VBC, and VCA with some angles. If we need to calculate the positive and negative components of phase voltages, then how can we proceed, sir? The line, positive and negative symmetrical components of line voltages, I calculated, sir. Just going on with the formula of 1/3 VAB plus alpha VBC in the same manner. But coming on to this phase voltages, I'm not able to proceed, sir, because he has given me VAB.
Phase voltage will become by √3. Listen.
Sir?
Phase voltage will become by √3, VA1.
Okay, sir.
VA1 value becomes by √3, right? VAB1 by √3.
Okay, sir.
Sridevi, are you listening to me?
Yes, sir. Yes, sir.
You can find out VA1, VB1, VC1, right?
VA1 is nothing but the addition of okay, sir. VA, I'm taking it as
VA1 equals to VAB1 by √3 at an angle of VAB1 angle minus 30 degree.
Sir, can you repeat? Sir, I didn't get it, sir.
So, for example, VAB1 value is something like 100 at an angle 20 degree volts.
Okay, sir. Okay, sir.
Then what is VA1? 100 by √3 at an angle of 20 degree minus 30 degree, right?
Yes, sir. Okay, sir.
Similarly, you find out VA2 also, then you add up VA1 and VA2.
Okay, sir.
Okay?
Okay, sir.
You don't know VA0. That's the issue there.
Yes, sir. VA0 he has not given.
VA0 we can't get.
I'm trying in another manner. VAB is equals to VA minus VB. Then also we don't have V0 and V1 and V2. So I'm not able to solve from there.
VA0 you don't get.
Yeah. Yes, sir. I'm
Because
not getting
line
it.
to line voltages are given, you don't have zero sequence voltage in that.
Yes, sir. Yes, sir. So I'm not able to calculate. Okay, sir.
So strictly speaking, we can't say what is the value of VA. But
Yes,
approximately we can say VA1 plus VA2 by neglecting zero sequence effect.
Okay, sir. Okay, sir. Okay. Okay, sir. Thank you, sir.
Okay. Any other doubts you have? Please raise your hands. Any other doubts? So I think I can leave for this day. Can I leave? Thank you.